Okay, let's unpack this. Have you ever considered how molecules, those fundamental building blocks of everything around us, perform a delicate dance, deciding whether to embrace new partners by adding groups across a double bond, or, conversely, to gracefully shed existing partners to form a new one?
It's a constant back and forth, isn't it?
It really is. It's a foundational piece of molecular choreography happening constantly, dictating how compounds are built and broken down.
It truly is. This is the very essence of organic chemistry, the precision engineering behind countless materials, medicines, and even biological processes. And today, we're going to pull back the curtain on this intricate molecular ballet.
Exactly. Here on The Deep Dive, our mission is always to be your shortcut to being well-informed. We take complex, often dense information and distill it into those essential, insightful, and frankly entertaining nuggets.
Getting you the core understanding without, drowning you in details.
Right. You're getting a deep dive without feeling overwhelmed by information overload.
And our source material for today's deep dive is a foundational text in the field. Chapter 5 of Advanced Organic Chemistry, Part A, Structure and Mechanisms, 5th ed. This chapter lays out the intricate world of polar addition and elimination reactions,
which are absolutely critical to understanding how organic molecules transform.
Absolutely essential.
So our mission for you today is to equip you with a deep yet accessible understanding of these crucial organic transformations. We'll be focusing on their core structures, the intricate reaction mechanisms that govern them, and even some surprising practical applications in the lab and beyond.
Yeah, and we'll definitely break down the jargon. We want you to see the real-world relevance here.
Definitely. Let's get started. When we talk about the dance of addition and elimination, we're really talking about two sides of the same coin, aren't we?
Exactly. Let's start with the basics, those addition reactions.
Okay. So imagine a carbon-carbon double bond. In a polar addition reaction, this double bond effectively reaches out and grabs two new groups, attaching them to adjacent carbons.
We call these vicinal groups, meaning they're neighbors, right?
Right, neighbors. And today, our focus is specifically on reactions that proceed via electrophilic polar mechanisms.
That's right. In these electrophilic additions, an electron-seeking molecule, which we can call an electrophile.
Something that wants electrons.
Exactly. It attacks the electron-rich double bond. Think of it like this. The double bond's pi electrons are eager to form a new connection. One part of the attacking molecule forms a bond to a carbon, then the other part, the nucleophile,
the one that brings electrons,
joins the adjacent carbon, completing the process. So you start with a CC double bond, and you end up with a CC single bond with two new groups attached.
Now, there are other types, radical additions and so on.
Right, but our deep dive today focuses on this electrophilic choreography.
And then there's the flip side of the dance. Elimination reactions.
The reverse process, basically.
These are about removing two adjacent groups from a molecule to form a new double bond. It's like those two partners who just joined the dance, deciding to gracefully exit, leaving a new double bond in their wake.
The most classic examples here are the E2, E1, and E1CB eliminations. These typically involve the removal of a hydrogen atom and another leaving group from neighboring carbons.
So a base comes in?
Yeah, picture a chemical base arriving, plucking off a hydrogen while simultaneously the leaving group departs, and a double bond forms between the two carbons. It's the exact inverse of adding those groups.
What's truly fascinating is how often these two processes, addition and elimination, are the former reverse of each other.
They really are linked. In some cases, they are perfectly reversible reactions under very specific conditions, almost like pressing rewind on a video.
Could you give an example?
A perfect illustration of this reversible relationship is the acid-catalyzed hydration of alkenes and the dehydration of alcohols.
Okay, adding water and removing water.
Exactly. If you add water to an alkene in the presence of acid, you generate an alcohol. But take that same alcohol, treat it with acid, and you can effectively remove water, regenerating the alkene.
So the conditions matter.
Hugely. The precise conditions, whether you're in an aqueous solution or distilling off the alkene as it forms, can subtly shift equilibrium, dictating which direction the reaction predominantly flows.
But it's not always a straightforward two-way street that easily reverses, is it?
No, definitely not always. Consider hydrophylogenation and dehydrophylogenation adding or removing something like HCl.
Okay.
While they represent an additional elimination pair for the same molecules, they usually don't reverse under identical conditions.
Right.
The addition of a hydrogen halide, like HCl, thrives in an acidic environment.
Right.
Whereas its removal, dehydrophylogation, typically requires a strong base. So, Same chemical players, but different environments call for completely different choreography.
This leads us to a crucial, almost philosophical concept in chemistry, the principle of microscopic reversibility.
Ah, yes, this is fundamental. Here's where it gets really interesting. This principle states that if a reaction is reversible under similar conditions, then its exact mechanism, meaning all the intermediate compounds and the fleeting transition structures that connect them, is identical in both the forward and reverse directions.
Okay, wait, so the pathway is exactly the same, just run forward or backwards?
Precisely. So any insights we gain about, say, an addition reactions pathway, perhaps involving short-lived charged intermediates.
Like carbocations.
Exactly. Those insights apply equally to its corresponding elimination reaction and vice versa. That reversible acid-catalyzed hydration and dehydration of alkenes with water is a prime example.
Okay.
Our sources show that two key fleeting chemical forms are involved: a carbocation, a carbon atom with a positive charge, and a protonated alcohol, an alcohol that has temporarily accepted an extra proton.
And it's the conditions that push it one way or the other.
Right. It's the reaction conditions, like the concentration of water versus removing the alkene by distillation, that act as the conductor, directing this equilibrium and ensuring the dancers move in the desired direction. Think of it like a path that can be walked forwards or backwards. The stepping stones and the temporary rest points along the way are precisely the same. It's just your starting point and final destination that change.
Got it. Okay, so when we zoom into these polar additions, are there general ways they happen, like different styles?
Yeah, we can identify 4 fundamental styles or limiting general mechanisms for how these reactions unfold. All of them involve an electron-seeking electrophile initiating the attack on the electron-rich pi bond of the alkene.
So the electrophile always starts the dance.
Always. This initial approach is typically perpendicular to the plane of the double bond, right where the electron density is highest, near the midpoint. The main differences between these mechanisms lie in how stable the intermediate is and the precise timing of when the second partner, the nucleophile, forms its bond.
Okay, what's the first style?
First, imagine a solo performance by the electrophile. This is mechanism A, sometimes called AD2. Here, the electrophile first breaks apart, or maybe it's already separate, like H plus A, forming a distinct positively charged carbocation that's free of its counterion.
Like it's floating on its own.
Pretty much. Think of it as a strong acid protonating an alkene, creating an unencumbered positive charge on a carbon. AD2 stands for addition, electrophilic, bimolecular, meaning 2 molecules are involved in the slow step.
Okay, what's next?
Next, we have mechanism B, a more tightly coupled duet. A carbocation still forms, but it's generated right alongside its counterion, existing briefly as an ion pair.
So it's stuck together almost.
For a moment, yeah. The reactivity here can be faster than if the ions had to completely separate, especially if the carbocation is reasonably stable and the electrophile isn't good at forming a temporary bridge. The 2 partners might combine to form the product before they ever truly drift apart. This is also considered an AD2 pathway.
Right. And the third style?
Our third style, mechanism C, is a synchronized partnership. Here, the electrophile bonds to both carbons of the alkene at the same time, forming a cyclic, 3-membered, positively charged intermediate, often called a bridged cation.
Like a little triangle.
Exactly, a temporary triangular embrace. The second step then involves the nucleophile breaking into this ring from the opposite side, and this leads to a crucial outcome. It nearly always results in stereospecific anti-addition.
Meaning the 2 new groups end up on opposite faces of the original double bond.
Precisely. This synchronized style is especially important when the electrophile can act as a bridging partner, like the halogens we'll discuss. This is another AD2 variant.
Okay, one more.
Finally, mechanism D. Picture a perfectly coordinated group routine. This is the ADE3 mechanism for addition, electrophilic, termolecular.
3 molecules involved now.
In the transition state, yes. It implies a truly simultaneous transfer of both the electrophilic and nucleophilic parts from 2 separate molecules of the reagent. This cleverly avoids forming a distinct charged intermediate.
And the stereochemistry.
Like the bridged mechanism, this also typically results in anti-addition. It often involves the alkene forming a preliminary complex with 1 reagent molecule, which then interacts with a second reagent molecule to complete the synchronized transfer.
So in terms of speed, what controls how fast these reactions go?
Good question. It can be either the initial formation of the bond to the electrophile, that first step.
Okay.
Or it can be the subsequent joining of the nucleophile to that charged intermediate. But in the AD3 group routine, where everything happens concurrently, well, both stages happen at the same pace. It's all one motion.
So what determines which dance style a particular reaction adopts? Which mechanism wins?
It really boils down to two things: the inherent nature of the electrophilic region itself, and the relative stabilities of the various intermediates that could potentially form.
Like H plus.
Exactly. For example, the proton, H plus S, is considered a hard electrophile. It's very small and has no free electrons available to participate in a temporary bridge. So, when it initiates the dance, it overwhelmingly prefers to form a simple, positively charged carbocation following those solo performance styles, A or B.
And fluorine is similar.
Fluorine, F plus S, behaves similarly, yeah.
But what about other electrophiles?
Then you encounter softer, more flexible, and more polarizable electrophiles. These partners are better at forming temporary bridges. Here, those bridged intermediates, like in our synchronized partnership style C, become much more prominent.
Like with bromine.
We'll see this extensively with ions formed by bromine in many bromination and chlorination reactions, and also with electrophiles involving sulfur and selenium. They like to bridge.
And the AD3, the three-molecule dance.
As for those group routine termomolecular collisions, the 8E3 mechanism, they're generally less likely unless there's some preliminary complex formation. It's hard for three things to collide perfectly at once. In reality, these reactions often exist on a continuum, blending elements of these limiting styles. Our goal in this deep dive is to highlight the common mechanistic features that tie these electrophilic additions together, while also recognizing the specific characteristics that each particular reagent brings to the molecular dance floor.
Okay, let's dive into some specifics then, starting with the addition of hydrogen halides to alkenes, like HCl or HBr. This reaction has been a cornerstone of understanding how molecules interact for decades.
Absolutely. One of the first things researchers noticed was its regioselectivity.
Meaning, if the alkene isn't symmetrical, where do the H and the X actually go?
Exactly. When an unsymmetrical alkene predominantly yields one of two possible structural isomers, we call that regioselective. And for hydrogen halides, the general observation is famously known as Markovnikov's rule.
Ah, yes, Markovnikov. So what does it state?
Markovnikov's rule states that in the addition of HX to an unsymmetrical alkene, the nucleophilic halide ion, that's the X, the negatively charged part, becomes attached to the more substituted carbon atom of the original double bond.
Okay, so the halogen goes to the carbon with more carbons attached.
Basically, yes. Or you can think of it as the hydrogen goes to the carbon that already has more hydrogens. The rich get richer in terms of hydrogens.
Why does that happen? What's the reason?
The fundamental basis for this preference lies in the stability of the fleeting intermediate formed. When the alkene gets protonated, a new CH bond forms from the pi electrons. If a carbocation, a carbon with a positive charge, is formed as an intermediate,
Which it often is with H plus cord.
right, protonation at the less substituted carbon leads to the more stable carbocation. Carbons with more branches attached are better at stabilizing that positive charge.
Makes sense.
And that more stable, positively charged intermediate is the one that preferentially reacts with the halide ion. Even if a fully separated carbocation doesn't explicitly form, the developing partial positive charge at the more substituted carbon still directs the regioselectivity, leading to the Markovnikov product.
Okay, but I remember there's a catch, especially with HBr.
Ah, yes. A crucial complication. Sometimes a completely different choreographer takes over, a free radical chain addition.
Radicals.
Yes. This can compete with the ionic pathway, especially if there are traces of peroxides or even just light. This free radical pathway leads to the anti-Markovnikov product, where the halide attaches to the less substituted carbon. The opposite outcome.
So how do you control that in the lab?
Good question. This is a significant consideration in practical synthesis. To minimize this radical pathway, you need to use very high purity alkene and solvent, exclude all light, and sometimes even add radical inhibitors. It's a fascinating alternative mechanism that we'll explore in depth in a future deep dive on radical chemistry.
Right. Now, in terms of how quickly these HX additions happen, is there an order?
Yes, hydrogen halides follow a predictable reactivity order. HI is the most reactive, followed by HBr, and then HCl. HCl reacts quite slowly with simple alkenes.
But chemists have tricks.
Yeah.
Right.
Always. Using solid adsorbents like silica or alumina can make these reactions much more convenient and often faster. With these solid supports, HBr, for instance, undergoes exclusively ionic addition, which gives you much better control over the product. No radicals.
And you don't always need the gas.
No, you don't always need gaseous hydrogen halides. Liquid sources like thionyl chloride, SOCl2, or oxalyl chloride, COCl2, Or even trimethylsilyl halides can generate HX in situ.
Meaning right there in the reaction.
Exactly. They create the hydrogen halide right there in the reaction mixture, often by reacting with residual water or hydroxyl groups on the adsorbent. This is a very practical method for getting the desired product without handling corrosive gases. Like adding COCl2 to an alkyl alumina gives a good yield of the alkyl chloride.
Now, you mentioned kinetics earlier. Are there any quirks there?
Oh, yes. Kinetic studies have unveiled some fascinating things. For many hydrogen halide additions, the reaction rate depends not just on the concentration of the alkene in HX, but sometimes on 2 molecules of HX. Yeah. So the rate often looks like rate equals calc in HX fossa. This third-order dependence has been observed for reactions involving HCl or HBr with various alkenes, like 2-methyl-1-butene or cyclohexene.
So what does that mean mechanistically, the 8E3 thing?
It points strongly to our 83 group routine mechanism. It means that in the crucial transition state, a proton is transferred from one HX molecule to the alkene, while the halide ion is simultaneously captured from a second HX molecule.
Like a coordinated attack.
Exactly. It's like the alkene forms a preliminary complex with one HX, and then a second HX molecule comes along to help complete the concerted transfer. Some people visualize it as an ion sandwich, where the acids anion and a halide ion are involved in facilitating the proton transfer.
Okay, let's shift to stereochemistry, the 3D arrangement. How do the H and X add spatially?
For alkenes that don't have special electron stabilizing groups, the addition of hydrogen halides is usually anti.
Opposite faces.
Right. The hydrogen and the halide add to opposite faces of the double bond. Imagine a molecular handshake where partners approach from opposite sides. This has been seen for HBr with things like cyclohexene or pimple-batunes, and for HCl with similar systems.
Why anti?
This anti-stereochemistry is consistent with a mechanism where the halide ion attacks the pi bond from the opposite side to where the proton is delivered, potentially involving that simultaneous interaction with HX we just talked about.
But it's not always anti.
No, it's important to remember that conditions like temperature and solving can influence this delicate balance. For instance, HCl addition to 1-uro-2-dimethylcyclohexene is anti at room temperature, but surprisingly becomes syn-dominant at very low temperatures, like -78 degrees C. It shows how subtly the dance steps can change.
Okay, now here's where it gets really interesting, I think. What happens when the double bond is connected to something that stabilizes positive charge?
Yeah.
Like a phenyl ring in styrene.
Ah, yes. A crucial shift in stereoselectivity happens then. When the double bond is conjugated with a carbocation stabilizing group, especially an aryl ring syn addition, where the hydrogen and halide add to the same face of the double bond, can significantly increase and even become the dominant pathway.
So, same side addition now. Why the change?
Exactly. This change points to an ion pair as the key intermediate. Because the carbocations formed in these cases, like benzoate carbocations, are more stable, thanks to stabilization from the aryl group, a perfectly synchronized attack by the halide isn't strictly required right after protonation.
The quinurcation can hang around a bit longer.
A little bit, yeah. And if this ion pair then collapses to form the product faster than the carbon bond can freely rotate, then syn addition occurs because the proton and halide ion are initially on the same side.
Is there evidence for this?
Yes. Kinetic studies on styrene with HCl support this. The reaction is first order in HCl, dependent on only one HCl molecule in the rate determining step, which is consistent with forming an ion pair rather than needing that second HCl for the 83 mechanism.
And we also see clear evidence for these short-lived charged intermediates through competing reactions with the solvent, right?
Absolutely. For example, if you add HCl to styrene and acetic acid, you don't just get the chloride product, you also get a small amount of acetate product.
Because the acetic acid jumps in.
Exactly. This clearly shows the solvent molecules are competing with the halide ion to capture that positively charged intermediate.
And adding extra salt helps the halide win.
Precisely. If you add extra halide salts, like lithium bromide or tetramethylammonium chloride, it increases the rate at which the halide ion captures the intermediate, further confirming the presence of a cationic species ready to react with available nucleophiles.
Okay, but maybe the clear signs of these carbocations are skeletal rearrangements.
Definitely. That's a classic indicator. If a hydrogen with its electrons or an alkyl group can shift within the intermediate to form a more stable carbocation, it often will. For instance, reacting CH3-2CH2 with HCl yields both the expected straight-chain chloride and a rearranged product where the chlorine is on a tertiary carbon.
Because the intermediate rearranged first.
Exactly. It's a telltale sign that a carbocation formed, shuffled its structure for greater stability, and then the halide added.
It's a bit of a paradox, though, isn't it? These rearrangements strongly suggest discrete, independently existing carbocations.
Right, like mechanism A or B.
Yet the kinetics sometimes show that third-order dependence, implying two HX molecules, are needed in the rate-determining step, like mechanism D. How does that work?
It is complex. It suggests maybe a scenario where a second HX molecule actually assists in the initial ionization, sort of helping pull the leaving group off. Or maybe it really is that halide-assisted protonation in that ion sandwich arrangement. This complex behavior of the generated cationic intermediates is very consistent with the general reactivity principles of carbocations we learned about before.
Okay, what about more complex systems like dienes or Norborn?
Right. Additions to dienes molecules with two double bonds, and even Norborn, a bicyclic compound, introduce their own set of complexities due to the unique charged intermediates they can form.
For dienes, you can get 1-2 addition or 1-4 addition, right?
Yes. 1-2 addition means the groups add two adjacent carbons of one double bond, while 1-4 addition means they add to the ends of the conjugated system. The stability of the allylication formed when a diene gets protonated makes the ion pair mechanism more favorable, although a polar reaction environment is still necessary. For example, 1-3-penadiene gives primarily the 1-2 addition product.
Any exceptions?
Interestingly, with 1-phenyl 1-3-betadiene, HCl adds exclusively via 3-4 addition to the double bond not connected to the phenyl ring. This allows the product to retain its very stable styrene-type conjugation. The kinetics for this are second order, consistent with forming a relatively stable carbocation, 8E2.
And Norborn. That one's always tricky.
Norborn is a particularly intriguing case. Factors like the inherent stability and easy rearrangement of the Norborn location come into play here. When deuterated hydrogen bromide, DBr, is added to Norborn, it gives exclusively the exonorbornyl bromide.
Exo meaning on the outer, less hindered face.
Correct. And studies tracing the deuterium atom show it ends up scrambled across multiple positions. 3 and 7 positions.
What does that scrambling tell us?
This exo-orientation and the scrambling of the deuterium atoms are strong evidence for the involvement of a highly rearranged, bridged Norbornyl completion. It's not a simple carbocation. Similar studies with HCl show almost exclusively the exochloride.
Is it perfectly symmetrical, though?
Not quite. The fact that the deuterium-labeled products are formed in unequal amounts suggests that a perfectly symmetrical bridged ion isn't the only intermediate. This indicates that some synaddition can also occur through ion pair collapse before the bridged ion fully achieves symmetry. Plus, known hydride shifts within the Norbornyl cation also lead to rearranged products, further complicating the picture.
Okay, so let's summarize HX additions. What's the big picture?
So, what does this all mean? The exact mechanistic pathway and the resulting stereochemistry are highly dependent on the starting alkane's structure. Alkanes that form relatively unstable carbocations are likely to react via that 83 termolecular complex, the group routine, and often exhibit anti-stereospecificity.
But if the cation is stable?
But if the alkane can form a more stable, positively charged intermediate, the reaction primarily proceeds via rate-determining protonation, ADE2, maybe ion pair, and the specific properties of that cation, its potential for rearrangement, how fast it gets captured, dictate the final product structure and stereochemistry. It's a beautifully nuanced interplay.
Okay, let's shift our focus now to acid-catalyzed hydration and related addition reactions. Basically adding water across the double bond to make alcohols.
Right, a fundamental process. At its simplest, you can view it as protonating the alkane to form a carbocation, which then eagerly reacts with water.
And that explains Markovnikov's rule again.
Absolutely. This straightforward mechanism explains why unsymmetrical alkanes predominantly yield the more highly substituted alcohol the water attacks, the more stable carbocation. However, there's more to it than just a simple carbocation. We need to consider if protonation is reversible, if the nucleophile water participates before proton transfer is complete, or if other carbocation reactions like rearrangements compete for attention.
What did early studies show? Like with styrenes?
Early studies on styrenes, which form quite stable benzylic carbocations, beautifully illustrated how electron-releasing groups on the phenyl ring dramatically increase the hydration rate.
Because they stabilize the positive charge.
Exactly. It correlates perfectly with their ability to stabilize a developing positive charge. Plus, a substantial solvent isotope effect, where the reaction is notably faster in regular water, H2O, than in heavy water, D2O, maybe 2 to 4 times faster, is a strong indicator that breaking a bond to hydrogen or deuterium is part of the crucial rate-determining step. It means proton transfer is slow.
And the water adding is fast.
Indeed. Water's capture of the resulting carbocation is usually very fast. This is demonstrated by how little deuterium is lost from an unreacted deuterated styrene early in the reaction. While the overall process is reversible, leading to eventual isotopic exchange if you let it sit long enough, the initial steps are clearly defined by that rate-determining protonation.
What about simple alkenes, like isobutylene?
Alkyl substituted alkanes like 2-methylpropene isobutylene or 2,3-dimethyl-2-butene behave similarly. Evidence like general acid catalysis and those solvent isotope effects also support rate-limiting protonation for them too.
You mentioned alkyl groups increase the rate. How much?
The impact of alkyl substitution on these hydration reactions is truly dramatic. Alkyl groups accelerate the reaction because they both boost the electron density of the double bond, making it more attractive to the electrophilic proton, and they stabilize that carbocation intermediate.
So it's a double benefit.
Right, and the effect is huge. To give you a sense of scale, Table 5.1 in the source shows relative rates. Compared to ethene, propene is 107 times faster, 2-methylpropene is 111 times faster. Adding just 1 or 2 more carbon branches can make the hydration reaction billions of times faster. It's like putting a rocket booster on a bicycle. Styrene is sort of intermediate in reactivity.
Wow. Does strain matter too?
Yes. And it's not just electronic effects. Strain also plays a role. Strained alkenes, like trans-cyclooctene, are significantly more reactive, maybe 2,500 times more reactive than the cis isomer in this case. This enhanced reactivity is attributed to the higher inherent energy of the strained alkene. That strain gets released and stabilized in the transition state of the reaction, lowering the energy barrier.
Okay, so water adds. What about other solvents, like alcohols?
Beyond water, other nucleophilic solvents can also add to alkenes under strong acid catalysis. For instance, alcohols can add to alkenes to form ethers, with a mechanism that closely parallels hydration.
Does the acid strength affect the outcome?
Yes, the strength of the acid plays a critical role in the stereochemistry. Stronger acids tend to favor discrete carbocation intermediates, which, because they can rotate before capture, can result in non-stereospecific addition. Mixtures of syn and anti.
But weaker acids?
Weaker acids might involve the solvent more intimately in an alkene acid complex. A great example is using DBr as a catalyst for adding acetic acid to Z or E2-butene. This gives stereospecific anti-addition, indicating a concerted ADE3 process where everything lines up perfectly. But switch to a stronger acid like triflaic acid, CF3SO3H, and you lose that stereospecificity, suggesting a more open, rotating carbocation, ADE2. This clearly reflects how much nucleophilic participation is needed to complete the proton transfer.
What about trifluoroacetic acid, TFA?
Trifluoroacetic acid, or TFA, is interesting because it's acidic enough to add to alkenes without needing an even stronger acid catalyst. Its mechanistic features are quite similar to strong acid-catalyzed water additions. It shows an isotope effect, correlates with substituent effects, sigma plus, and frequently causes rearrangements.
Rearrangements, again, sign of a carbocation.
Exactly. Like with 3-methyl-1-butene, TFA addition gives rearranged products strong evidence for a carbocation intermediate briefly forming and shuffling its atoms.
And what about things like vinyl ethers? They seem like they'd be really reactive.
They are. We can't forget vinyl ethers. These compounds exhibit greatly enhanced reactivity of their carbon-carbon double bonds towards acid-catalyzed addition, thanks to their powerful electron-releasing oxygen group. The oxygen pumps electrons into the double bond.
What products do they form?
While the initial addition products are often unstable hemiacetyls that decompose to a ketone and an alcohol, the crucial protonation step is still rate determining. Kinetic data like general acid catalysis and solvent isotope effects confirm a mechanism very similar to simple alkene hydration.
Okay, let's move on. Next up, the addition of halogens to alkenes. Bromine and chlorine.
Right. Alkene chlorinations and brominations are incredibly general and synthetically useful reactions in organic chemistry, and studying their mechanisms has given us even deeper insights into these electrophilic dances.
Fluorine is too crazy, iodine too reversible.
Pretty much. While reacting elemental fluorine with alkenes is often too violent and iodination is easily reversible under many conditions, the trends observed for chlorination and bromination beautifully illustrate the general behavior of all halogens. The overall reactivity order follows the halogen's size and electronegativity, F2Cl2, Br2, I2.
What's the very first step in, say, bromination?
The first graceful step in bromination is the formation of a weak, temporary embrace a pi complex between the alkene and the bromine molecule.
Like you just get close first.
Exactly. These weak complexes have been known for a long time. Their role as intermediates is confirmed because you can actually observe them spectroscopically, and their rate of disappearance perfectly matches the rate of the final bromination product's formation.
And after the pi complex, what's the intermediate?
The next crucial step is the formation of a positively charged intermediate. This can be either a bridged bromonium ion, that three-membered ring with bromine as one of the atoms, or a more open beta-bromo-carbocation, which is a carbon with a positive charge next to a carbon bonded to bromine.
How does it choose? Bridged or open?
Which one forms depends on how stable the potential carbocation would be. For most simpler carbon chain systems, the bridged bromonium ion is favored. However, with styrenes, it's a borderline case.
Because of the phenyl ring.
Right. If the phenyl ring has electron-releasing groups, it can stabilize a full open carbocation enough for it to form. But electron-withdrawing groups will push it towards the bridged intermediate.
Does solvent matter here?
Hugely. Because this step involves forming charged species, it's highly sensitive to the solvent. Switching from a non-polar solvent like carbon tetrachloride to a slightly more polar one like 1-ur-2-gichloroethane can accelerate cyclohexene bromination by a factor of 100,000. It's like moving from a sticky dance floor to a slick one.
You mentioned complex kinetics for HX addition. Is it the same for bromine?
Yes, bromination kinetics are often quite complex, with several distinct pathways contributing to the overall speed of the reaction. The rate expression can involve terms that depend on the alkene and 1-bromine molecule, K1 term, or the antonin 2-bromine molecules, K2 term, and even the alkene 1-bromine and a bromide ion, K3 term.
Yep. So rate equals K1 alkene Br2 plus K2 alkene Br22 plus K3 alkene Bar. Wow.
It can be that complicated, yes. In a solvent like methanol, if there's a high concentration of bromide ion present, that third term involving Dr can dominate the reaction rate. In non-polar solvents, it's usually the first two terms involving 1 or 2 bromine molecules that are most important.
What's the mechanism for that third-order reaction, the K2 term with 2 bromines?
It's fascinating. It's thought to be similar to the first-order pathway, but a second bromine molecule, or a bromide ion, assists in converting the initial weak pi complex into that charged intermediate, the ion pair. There's a strong quantitative correlation between these second and third-order processes, suggesting very similar underlying choreography.
Do impurities matter?
Yes. It's also worth noting that common impurities like HBr, which can form from Br2, and even water can significantly accelerate bromonium ion formation, often dominating the reaction under normal preparative conditions unless you're extremely careful.
Is chlorination simpler?
Chlorination kinetics are generally simpler, usually second order overall. First order in alkene, first order in chlorine.
How do substituents on the alkene affect the rate? More branches, faster reaction?
Yes. When we look at how different alkyl groups on the alkene affect the speed of halogenation, we see that adding more alkyl groups increases the reaction rate, as you'd expect for an electrophilic process. Table 5.2 gives some relative reactivities. The rate increase is substantial, though maybe not as dramatic as for protonation.
Solvent dependent.
Very solvent dependent. The transition state has high ionic character, which is reflected in correlations with solvent polarity scales like the Winstein-Grunwald Y values.
What about electronic effects, like on styrenes?
Studies using Hammett correlations for bromination of substituted styrenes show a highly negative rho value, around MEDH 4.8 when correlated with sigma plus constants. This value is significant because it strongly confirms a very strong demand for electrons in the crucial transition state, highlighting the highly electrophilic nature of the mechanism.
Okay, back to stereochemistry. Does the intermediate dictate whether it's syn or anti-addition?
Absolutely. Stereochemical studies provide crucial information. For brominations, anti-addition is generally preferred for alkenes without strong carbocation stabilizing groups.
Opposite faces again.
Right. This means the two new bromine atoms end up on opposite faces of the original double bond. However, if the alkene is conjugated with an aryl group, syn addition, where the bromines add to the same face, becomes more prevalent, sometimes even dominating. Chlorination tends to follow a similar pattern, though it's typically less stereospecific than bromination. Table 5.3 shows some examples.
So bridged ion means anti. Open cation means maybe syn or mixed.
That's the general interpretation. When a bridged bromonium ion is involved, anti-stereochemistry is easily explained. The nucleophilic bromide ion attacks from the backside, opening the ring and leading to anti-addition, like a perfectly choreographed pirouette. If, however, a freely rotating open beta-bromocarbocation forms, then both syn and anti-products are possible, as the carbon bond can spin.
And if the ion pair collapses fast?
Right. If an ion pair collapses to product faster than the carbon bond can rotate, syn addition can predominate.
What about solvent effects on stereochemistry?
Even in nucleophilic solvents, where the solvent might compete with bromide to attack, anti-stereoselectivity often persists unless those strong electron-releasing groups are present. This anti-preference can arise not just from a long-lived bridged ion, but also potentially from very fast capture of a short-lived carbocation intermediate before it rotates. The lifetime of the cyclohexane bromonium ion in methanol has been estimated at around 10 seconds, very short, but maybe 100 times longer than typical secondary carbocations.
Is chlorine different from bromine in bridging ability?
Yes. Chlorine is generally considered a poorer bridging group than bromine. It's less polarizable and more resistant to holding a positive charge. Comparing the bromination versus chlorination of EZ1 phenylpropene in Table 5.3 really shows this. Bromination is strongly anti-dominant, while chlorination is actually slightly syn-preferred, suggesting styrenes react with chlorine via ion pair intermediates more readily.
This idea of bridged ions sounds compelling, but is there actual proof? Can we see them?
Yes. What's truly fascinating here is that we have direct evidence for the existence of these bridged polonium ions. For example, specific bromonium ions formed from propene and related alkenes can actually be observed directly by NMR spectroscopy under very strong acid conditions, superacid, allowing chemists to literally see these fleeting intermediates.
Yeah.
A bromonium ion from 2-3-dimethyl-2-butene has also been formed this way.
Wow, anything else?
Even more spectacularly, a highly bulky alkene called adamantylite and adamantane forms such a stable bromonium ion that it literally crystallizes out as a tribromide salt.
You can hold it in a bottle.
Well, carefully. It doesn't react further because of extreme steric hindrance. It's too crowded for anything else to approach. An X-ray crystal structure, shown conceptually in Figure 5.2 of this compound, confirmed its cyclic, bridged nature, a powerful visual testament to its existence.
Amazing. Have other polonium ions been crystallized?
Yes, similar crystal structures have been obtained for chloronium and iodonium ions too. These structures often show that the bridging is somewhat unsymmetrical, especially for chlorine, hinting at an inherent slight bias in the three-membered ring structure. You can also see the carbon-carbon bond lengthening significantly in the crystal structures, from a typical double bond length of around 1.35 A to maybe 1.45 per 54515 AO, showing how the electrons are being shared across the bridge.
Can these bridge ions go backwards? Can they fall apart again?
Yes, the reversibility of polonium ion formation has also been demonstrated, particularly for highly hindered alkenes where the follow-up nucleophilic capture is slow. Even a bromonium ion formed from cyclohexene can apparently release the original Br2 molecule when reacted with excess bromide ions. How do we know? Because this free bromine can then go on to brominate a more reactive alkene, like cyclopentene, if it's added to the mixture. It proves the dynamic nature of these intermediates.
Are there other ways to add bromine besides using Br2?
Yes, reagents like pyridinium bromide tribromide or tetrabutylammonium tribromide supply bromine effectively as the tribromide ion, Br3. They react via the initial Br2 alkene complex and generally show a strong preference for anti-addition.
Okay, this halogenation stuff is complex. Let's try to synthesize it. What's the overall picture?
Right. Here's where it gets really interesting, trying to tie it all together. Bromination typically involves that preliminary complex, which then collapses to an ion pair intermediate. Ionization creates charge separation and is assisted by the solvent, acids, or even that second Br2 molecule.
And the intermediate can be open or bridged.
Exactly. The resulting positive intermediate can be either an open beta carbocation, especially with styrenes or stabilizing groups, or a bridged bromonium ion.
And the stereochemistry follows from that.
Yes. Reactions that proceed primarily via bromonium ions are stereospecific anti-additions. But those that proceed through open carbocations can be syn-selective if the ion pair collapses fast, or even non-stereospecific if rotation occurs. It's truly a rich and varied landscape.
What about the synthetic side? Halohydrons.
Yes. Synthetically, halogenation with a nucleophilic solvent like water is incredibly important for making halohydrons, such as chlorohydrons and bromohydrons.
How do you make them typically?
Common reagents include things like chloramine T for chlorohydrons, or N-bromosuccinimide, NBS, and aqueous acetone, or THF, for bromohydrons. DMSO is also a good solvent.
Where does the water at?
Markovnikov.
Yes, the regioselectivity usually follows Markovnikov's rule. The nucleophile, water, is introduced at the more substituted position, consistent with attack on the intermediate where positive charge is better stabilized, or where the bridged ion is weaker.
Can you make iodohydrons?
Yes, iodohydrins can be made using I2 or specialized reagents. A mix of periodic acid, H5IO6, and sodium bisulfite generates hypoious acid in situ, giving good yields with high anti-stereoselectivity. Interestingly, nearby hydroxy groups can sometimes direct the addition to the more remote carbon.
How regioselective is the opening of the bridged ion?
Studies looking at the opening of halonium ions, for instance in methanol, show complete anti-stereospecificity for dissubstituted alkenes, whether methanol or bromide attacks. For monosubstituted alkenes, though, it's often not highly regioselective. There's competition between addition at the mono and unsubstituted carbons, likely due to conflicting steric and electronic effects. Strong bridging, especially in chloronium ions, can sometimes even lead to more anti-Markovnikov product for simple alkenes.
Does substitution ever happen instead of addition?
Yes, sometimes alkenes react with halogens to give substitution products instead of addition. For example, with 11,1-diphenolethene, substitution, loss of a proton, is the main reaction at low bromine concentrations. This happens when proton loss from the intermediate is faster than bromide capture.
Characteristic of carbocations again.
Exactly. Similarly, in chlorination, proton loss or even alkyl migrations can compete with addition, especially with alkanes like 2-methylpropene or 2-phosphor-3-dimethyl-2-butene that can form relatively stable tertiary carbocations or rearrange to them. This is more likely to occur in chlorination than bromination because chlorine is a weaker bridging partner, allowing for more carbocation-like character in the intermediates.
What do computers say about all this? Computational studies.
Computational studies have weighed in extensively on halonium ions. Gas phase calculations generally find that forming completely charged, isolated halonium ions from halogens and alkenes is energetically very difficult. They aren't usually stable on their own by calculation.
Does that match experiments?
Well, it highlights the importance of solvent stabilization. Early calculations sometimes predicted unsymmetrical bromonium ions, but higher-level calculations generally support bridge structures for chlorine and bromine, but not fluorine. The calculations consistently agree with the experimental trend that the ability to form a stable bridged ion increases as you go down the halogen group, FClBr.
Do they get this ability right?
They often underestimate the stability of these bridged ions compared to their behavior in solution, but they help confirm the fundamental trends and structural features, like calculated bond lengths, Cc around 1.4780, Cbr around 1.99A in one study. They also show how charge as distributed fluorine ends up negative, while chlorine and bromine are positive in the bridged ions. And they capture differences between systems, like cyclohexene favoring open cations more than cyclopentene, which agrees qualitatively with NMR.
Okay, what about fluorine and iodine specifically? Less studied.
Much less understood due to their extreme reactivity or reversibility. Elemental fluorine reacts violently with alkenes, but you can achieve electrophilic additions using specialized reagents like xenon difluoride or highly dilute F2 at low temps.
What's the stereochemistry?
Critically, these reactions often show syn stereochemistry, meaning the fluorine atoms add to the same face of the double bond. This syn outcome suggests a rapid collapse of a beta-fluorocarbocation fluoride ion pair, with a stable bridged fluoronium species appearing unlikely. Acetyl hypofluorite also gives predominantly syn addition.
And iodine?
Iodination, on the other hand, is easily reversible, and while generally stereospecifically anti, its exact mechanism, polar versus radical, isn't entirely clear under all conditions.
One last thing on halogens. Downs again. 142 versus 144 addition.
Right. Conjugated dienes reacting with halogens can yield either 1-4 addition or 1-4 addition products. Molecular bromine, Br2, in a chlorinated solvent, for example, typically favors the 1,4,4 product for simple dienes like butadiene, maybe around 7.1.
Can you change that ratio?
Yes. Milder brominating agents like pyridine-bromine complexes or the tribromide ion, Br3, tend to shift the product distribution to favor the 1-2 product.
Why the difference?
This shift is thought to be because molecular bromine often reacts through a cationic intermediate, leading to the thermodynamically favored 1-4 product under some conditions, while the less reactive agents involve a process more akin to the 83 anti-addition mechanism, cleverly avoiding the formation of those short-lived allelic cations and giving the kinetically favored 1-2 product.
What about the stereochemistry of diene addition?
It's complex. Bromination is often stereospecifically anti for the 1-2 addition product, but can be syn for the 1-4 addition product. Chlorination shows much less stereospecificity overall. It seems chlorination likely proceeds via ion pair intermediates, while bromination involves competing stereospecific anti-1-2 addition and carbocation pathways leading to syn or anti-products.
Phew, okay. Halogens covered. Let's transition now to sulfur and selenium. Sulfonylation and selenylation.
Right. These are electrophilic additions involving sulfur and selenium reagents, which are often used in organic synthesis. These reagents, like sulfonyl chlorides, RSCl, or organoselenium compounds, or SX, where X is electronegative, are designed to deliver an electrophilic sulfur or selenium atom to the double bond.
Are there many types of reagents?
Yes, Scheme 5.1 in the text lists quite a few examples, things like ornisulfonyl chlorides, phosphonium salts derived from thiols, N-phenylselenyl phthalimide. There are also methods to generate sulfonyl electrophiles from sulfoxides or selenylation reagents oxidatively from diphenyl diselenide using oxidants like DDQ or persulfate. These can be used to make useful hydroxy or methoxyselenylation products.
So for sulfonylation with RSCl, what's the intermediate, like halogens?
By analogy to halogenation, positively charged three-membered rings containing sulfur called thuranium ions can be important intermediates. Some have even been characterized. There's also mention of tetravalent sulfur compounds called sulforanes potentially being involved.
Is sulfur as electrophilic as chlorine?
No, sulfur electrophiles are generally less electrophilic than chlorine. For example, the rate acceleration going from ethene to a highly substituted alkene like 2-3-dimethyl-2-butene is only about 100-fold for sulfonylation compared to maybe 106 for chlorination or 107 for bromination.
How do substituents affect the rate?
It's complex. Electron-withdrawing groups seem to favor the initial complexation, while electron-releasing groups favor ionization to the thyranium ion, if that's the rate-determining step.
Does sulfur bridge strongly?
Yes. Unlike chlorine, sulfur is less electronegative and more polarizable, so it forms a stronger, more stable bridged intermediate, the thyranium ion, rather than an open carbocation, especially for alkenes without strong electron-releasing groups that could stabilize an open positive charge.
And what does that strong bridging mean for the outcome?
Regiochemistry.
It leads to some interesting regiochemical outcomes. Sulfonylation is often weakly regioselective and can even show a preference for anti-Markovnikov addition.
Opposite of Markovnikov.
This is usually attributed to steric factors. When the bridging is strong, the subsequent nucleophilic attack is directed to the less substituted carbon because it's simply more accessible. Table 5.4 shows data for propene and other alkenes supporting this.
And stereochemistry. Anti.
Consistent with those strongly bridged intermediates, the stereochemistry is typically anti-addition. However, with highly stabilizing electron-releasing substituents, like on 4-methoxyphenylstyrene, a loss of stereospecificity is sometimes observed, suggesting a more open carbocation-like character is introduced in those cases. Using a more electrophilic sulfonyl group, like trifluoroethylsulfonyl, shifts regioselectivity back towards Markovnikov, but maintains anti-stereospecificity, still a bridged intermediate.
What about computational models?
Computational modeling G2 level of simple HSX plus additions showed no gas phase barrier, with the electrophile approaching the midpoint of the pi bond, similar to halogenation. The reaction becomes more favorable as the leaving groupability of HX increases.
Okay, how about selenylation? RSX, is it useful?
Very useful. Selenylation reagents are incredibly useful in synthesis because the selenium-containing products aren't always the final compounds. The selenyl group can be later removed, reductively or oxidatively, or undergo other transformations to build complex molecules. Beta-selenylation of carbonyl compounds, for example, is a very important reaction sequence in synthetic chemistry, often used to introduce double bonds next to carbonyls.
What's the mechanism like? Bridged ions again?
Yes, mechanistically, reactions with arynoselenyl chlorides are accelerated by electron-releasing groups on the urosundinides. This is interpreted as involving a concerted addition where ionization of the C-Lil bond leads to C-Cl bond formation. Bridged selenuranium ions are key intermediates.
How reactive are they compared to halogens?
Alkyl substitution on the alkene enhances reactivity, but the effect is very small compared to halogenation. Table 5.5 shows this. Selenylation also seems particularly sensitive to steric effects. For example, a bulky phenyl substituent on the alkene can actually slow down the reaction, possibly due to both steric hindrance and the alkene's initial ground state stabilization. The Hammett rho value is typically small and negative, -0.7-ish, indicating only modest electron demand in the transition state. Sometimes positive rho values are even seen.
Regiochemistry. Anti-Markovnikov again.
Often, yes. Terminal alkenes frequently show anti-Markovnikov regioselectivity for selenylation, especially under kinetic control. However, rearrangement to the thermodynamically more stable Markovnikov product can be facile. Styrene, on the other hand, is regioselective for the Markovnikov product, likely because the phenyl group weakens the bridging effect, allowing for more positive charge development on the carbon closer to the phenyl group.
And stereochemistry, still anti.
Predominantly, yes. Seleneration is typically a stereospecific anti-addition for acyclic alkenes. Cyclic alkenes, like cyclohexenes, preferentially undergo diaxial addition, and bicyclic compounds like norborne exhibit highly stereoselective exo-anti-addition, which strongly points to an exo-bridged intermediate.
Can substituents influence the regiochemistry in norbornes?
Yes, polar substituents on norbornes can subtly control regiochemistry. Electron withdrawing groups tend to direct the incoming nucleophile to the carbon more remote from them. This is consistent with an unsymmetrically bridged selenoranium intermediate where the partial positive charge develops further away from the electron withdrawing group. Computational modeling also supports this, attributing selectivity to the ease of nucleophilic approach on a strongly bridged ion, or, for styrene, showing unsymmetrical bridging leading to Markovnikov selectivity due to greater positive charge at the benzylic carbon.
Okay, so let's broadly compare SC and halogens. What are key takeaways?
The key insights are: 1. Sulfur and selenium electrophiles are generally less electrophilic than halogens. 2. They are characterized by forming more strongly bridged intermediates. 3. This is consistent with their reduced sensitivity to electronic effects from alkyl or aryl substituents on the alkenes. Charge is delocalized in the bridge. 4. This also explains their increased tendency to exhibit anti-Markovnikov regiochemistry, steric attack on the less hindered side of the strong bridge. 5. And naturally, those strongly bridged intermediates strongly favor anti-stereochemistry.
Got it. Okay, next up, epoxidation. Adding an oxygen atom across a double bond to make an epoxide.
Right, a unique type of electrophilic addition. It's closely analogous to halogenation, sulfonylation, and selenylation because the initial electrophilic attack still forms a three-membered ring.
But the product is different, right?
Yes, here's the key distinction. The resulting epoxides are neutral and stable. They can typically be isolated and stored, unlike those highly reactive charged intermediates we've been discussing.
So what's the overall transformation?
The overall pattern is that you're effectively adding an OH plus equivalent and a nucleophile across the double bond. And importantly, the regiochemistry of subsequent ring opening, which we'll get to, is usually controlled by where the nucleophile can easily attack, meaning the oxygen is typically introduced at the more substituted carbon in the initial epoxidation step if you think about the overall hydration process.
What reagents do this?
The most common reagents for this involve peroxycarboxylic acids, like the widely used metachloroperoxybenzoic acid, or MCPBA. Others include magnesium monoperoxyphthalate, peroxyacetic acid, peroxybenzoic acid, and the very reactive peroxytrifluoroacetic acid. There's also oxone, which is potassium hydrogen peroxysulfate, convenient for aqueous epoxidations. These are powerful reagents, though it's important to remember that peroxyacids require careful handling due to their potential for instability or explosiveness.
What's the mechanism? Is it like the others, ionic?
No, and this is truly fascinating. Crucially, no ionic intermediates are involved in epoxidation.
Really? How do we know?
Well, the reaction rate isn't very sensitive to solvent polarity, which argues against charge buildup. And you consistently observe stereospecific syn addition.
Syn addition. So the oxygen adds to the same face of the double bond.
Exactly. Both new CO bonds form on the same side.
So if it's not ionic, how does it happen?
This all points to a concerted process. Everything happens in one synchronized step. It's often visualized with a proposed spiro transition state. Imagine the peroxy acid approaching the double bond not head-on, but sort of sideways, like a key twisting into a lock. The peroxy acid's OO bond plane is roughly perpendicular to the plane of the developing epoxide ring, and the oxygen atom transfers from this spiro position, forming the epoxide ring in one clean, synchronized move, often called the butterfly mechanism.
How does the alkene structure affect the rate?
When we look at structure-reactivity relationships, we find that alkyl groups and other electron-releasing groups increase the epoxidation rate. They make the double bond more electron-rich and therefore more attractive to the electrophilic peroxy acid. Conversely, electron-withdrawing groups on the peroxy acid itself increase its reactivity, making it a stronger electrophile.
What about electron-poor alkenes?
Double bonds that are conjugated with strong electron-withdrawing groups show low reactivity towards epoxidation, often requiring very reactive peroxy acids, like trifluoroperoxyacetic acid.
Does strain matter?
Yes, the presence of strain in the alkene actually increases its reactivity. For instance, norborne is about twice as reactive as cyclopentene, and transcycloctene is maybe 90 times more reactive than cyclohexene. This makes sense, as the reaction relieves some of that inherent molecular tension. There's also a good correlation between the relief of strain, calculated using molecular mechanics, and the epoxidation rate. It also correlates well with the alkene's ionization potential.
What about aryl groups, like in styrene? Does that speed it up?
Interestingly, no. Alkenes with aryl substituents, like styrene, are actually less reactive than simple unconjugated alkenes towards epoxidation.
Why is that? Aryl groups usually stabilize positive charge.
Exactly. The fact that they slow down epoxidation is strong evidence for a lack of significant positive charge or carbocation character in the transition state. If a carbocation were forming, those aryl groups would stabilize the transition state and accelerate the reaction, not slow it down. Here, the ground state stabilization of the conjugated styrene outweighs any stabilization in the TS.
Okay, what about stereoselectivity? Where does the oxygen add in 3D space?
The stereoselectivity of epoxidation has been extensively studied. For molecules without specific directing groups, oxygen typically adds from the less hindered side, simple steric control.
Like norborne giving exo product.
Precisely. Norborne gives a huge preference, like 96.4 for the exo product, simply because that's the more accessible face. Methylene cyclohexenes show a small preference for axial attack, addition to the equatorial face.
But are there stronger directing effects?
Oh yes. Here's a powerful effect that can override simple steric hindrance. The hydroxy directing effect.
From an OH group?
Yes. If there's a hydroxyl group present elsewhere in the molecule, it strongly favors the approach of the peroxy acid from the side of the double bond closest to it.
Why? How does that work?
It's believed to happen because the hydroxyl group can form a temporary hydrogen bond with the peroxy acid reagent in the transition state, stabilizing it. This interaction acts like a little tether, guiding the reagent to the nearby face. This is such a strong effect that it can even direct the epoxidation to occur on a sterically more hindered face.
Wow. Does it work for other groups?
Yes, other hydrogen bonding substituents like amides also show a syn-directing effect, and interestingly, it operates even in alkaline epoxidation conditions as well, where the alcohol group itself supplies the hydrogen bond donor.
What about allylic alcohols?
For allylic alcohols, the conformation of the alcohol chain is key. Epoxidation typically proceeds through a specific transition state, TSA in the book's diagrams, leading to high diastereoselectivity, like 9.1, mainly due to minimizing steric interactions in the alternative transition state, TSB.
Are there other subtle electronic effects?
In sterically unbiased systems, there's some evidence that electron-withdrawing groups tend to be syn-directing, while electron-releasing groups are anti-directing, although these effects are generally small. The exact origin, whether it's stereoelectronic or electrostatic, is still debated.
What do computational studies show about epoxidation?
They consistently confirm that spare a transition state model for various alkenes like ethene, propene, and norborne. They also correctly predict how different substituents affect the energy barrier, activation energy EA, for the reaction. They explain these effects in terms of less synchronous bond formation, meaning the new CO bonds form at slightly different rates, not perfectly simultaneously depending on the substituents.
So the TS can be unsymmetrical.
Yes. Figure 5.3 shows calculated geometries. With electron-releasing groups, like in propene or methoxyethene, the transition states become somewhat unsymmetrical. With an electron-withdrawing group like an acrylnitrile, the TS is even more unsymmetrical, with a significantly shorter bond forming to one carbon, reflecting the electronic influence and a higher energy barrier. It suggests the nucleophilic character of the peroxidic oxygen towards the beta carbon is important in some cases.
Okay, you mentioned peroxy acids. What about dimethyldeoxyrane, DMDO?
Ah, yes. DMDO is another incredibly versatile and synthetically useful epoxidizing agent. It's typically generated in situ, meaning right there in the reaction mixture, by reacting acetone with oxone, potassium peroxymonosulfate, in a buffered aqueous solution.
Can you isolate it?
Remarkably, yes, you can distill it as a dilute solution, around 0.1 mmol in acetone, or get higher concentrations by extraction. There are also improved methods for generating it in situ using phase transfer conditions.
What's its mechanism, similar to peroxy acids?
Computational models show a concerted mechanism very similar to peroxy acids, that spiral butterfly transition state again. Kinetics and isotope effects are also consistent with this.
Is it more or less electrophilic?
DMDO is generally considered somewhat less electrophilic than something like performic acid, based on calculations of electron density transfer. Interestingly, for electron-poor alkenes like acrylonitrile, the calculations suggest the DMDO oxidation transition state actually has a dominant nucleophilic component from the oxygen.
Is it sensitive to sterics?
Fairly sensitive, yes. Z-alkenes, where the bulky groups are on the same side, are usually more reactive than E-isomers. This is thought to be because the reagent can approach the Z-isomer while avoiding the alkyl groups more easily. For example, Z3-hexene reacts over 8 times faster than E3-hexene with DMDO.
Does it show directing effects?
Yes. Just like peroxycarboxylic acids, DMDO epoxidations are subject to cis or syn stereoselectivity guided by hydroxy and other hydrogen bonding functional groups, with the effect being strongest in nonpolar solvents.
Can you make more reactive versions?
Yes. Using more electrophilic ketones to generate the dioxarane yields more reactive reagents. For example, using 1,11,1,1-trifluoroacetone gives 3-methyl-3-trifluoromethyldeoxarane, which is much more potent. Hexafluoroacetone and even certain piperide and 4,1 salts can also function as catalysts with the charged nitrogen-enhancing reactivity.
So once you have the epoxide, what can you do with it? Ring opening.
Exactly. Epoxides, once formed, are incredibly useful building blocks in organic synthesis. Their inherent stability and controlled reactivity allow for the precise introduction of additional functionality in a predictable way. Because epoxide ring opening is often stereospecific, these reactions are great for establishing exact spatial relationships between adjacent substituents and complex molecules.
How do you open the ring? Acid or base?
The epoxide ring can be opened under either acidic or basic conditions, and fascinatingly, the regiochemistry, meaning which carbon the nucleophile attacks, depends critically on whether steric or electronic factors are dominant.
Okay, let's take base first.
In base-catalyzed reactions, the reaction is driven by the nucleophile attacking the epoxide. It attacks the less substituted carbon, as this is sterically more accessible.
Yeah.
Think of it like taking the path of least resistance. This results in anti-Markovnikov regioselectivity.
And under acid conditions.
Acid-catalyzed reactions are more nuanced, offering a choice at a molecular fork in the road. First, the acid protonates the epoxide oxygen. This makes the oxygen a better leaving group and weakens the carbon-oxygen bonds, allowing even weak nucleophiles to attack.
But which carbon gets attacked?
It depends. If the carbon-oxygen bond is still largely intact at the transition state, more SN2-like, the nucleophile will attack the less substituted position due to steric reasons, similar to base catalysis. But if the carbon-oxygen bond rupture is more complete at the transition state, more SN1-like, allowing a significant positive charge to develop on carbon.
A carbocation-like character.
Exactly. Then the nucleophile attacks the more substituted position because that carbon can better stabilize the developing positive charge. This leads to Markovnikov regioselectivity due to electronic control.
Is there evidence for this difference?
Yes, plenty. Kinetic and isotopic labeling studies have beautifully supported these fundamental aspects. Reaction rates for acid-catalyzed opening increase with additional alkyl substitution on the epoxide ring. For example, a 2,2-dimethyl derivative is much more reactive, clearly indicating that carbocation-like character is developing. pH rate profiles provide specific rate constants for the acid-catalyzed, uncatalyzed, and base-catalyzed pathways. And isotopic labeling shows that nucleophilic attack can occur at both the more and less substituted carbons, depending on the conditions and the specific epoxide.
What about the stereochemistry of opening?
Importantly, the opening of simple cis and trans-desubstituted epoxides like 2,3-dimethyloxarane in solvents like methanol or acetic acid under acidic conditions is often a stereospecific anti-addition. The nucleophile comes in from the backside relative to the oxygen.
Does an aryl group change things, like with styrene oxide?
Yes, the presence of an aryl substituent profoundly influences the regiochemistry in acid-catalyzed opening. It strongly favors cleavage of the benzylic CO bond due to electronic stabilization of the developing positive charge at the benzylic carbon. So, for styrene oxide, under acidic conditions, bond breaking occurs exclusively at the benzylic position. But under basic conditions, where sterics dominate, ring opening happens at both epoxide carbons.
Can Lewis acids also open epoxides?
Yes, Lewis acids like SnCl4 or BF3 can catalyze epoxide opening, for instance, methanolysis. They often show 95% attack at the benzyl carbon if present, with high inversion of configuration. This stereospecificity points towards a concerted nucleophilic opening of the Lewis acid-complexed epoxide, with bond-weakening electronic factors determining the regiochemistry.
Is there direct evidence for actual carbutions were forming during acid opening?
Yes, particularly with aryl epoxides. For epoxides derived from 1-aryl cyclohexanes, adding azide ion during acid hydrolysis can trap the intermediate. The fact that you get both cis and transdiol products, along with azide products, is exactly what you'd expect if a planar carbocation intermediate formed and could be attacked from either face.
Any other examples?
Dihydronaphthylene epoxides provide a nice contrast. The unsubstituted compound gives exclusively the transdiol upon hydrolysis, suggesting nucleophilic participation from water prevents a free carbocation. But the 6-methoxy analog, which can form a more stabilized carbocation, gives a substantial amount of rearrangement product, and the diol formed is a mixture of cis and trans stereoisomers. This indicates the stabilized carbocation has a significant lifetime, allowing for loss of stereochemistry.
What about simple saturated epoxides reacting with HBr or HCl?
For something like propylene oxide reacting with HBr, the halide adds preferentially to the less substituted primary carbon, giving the anti-Markovnikov product. This is typical for SN2-like attack under acidic conditions on less substituted epoxides. However, substituents that can stabilize a carbocation can reverse this preference.
Okay, let's summarize epoxides. They're stable, but you can open them.
Right. Epoxides are stable, isolable compounds. And critically, both the stereochemistry and regiochemistry of their ring opening can be precisely controlled by adjusting reaction conditions. If the ring opening is dominated by the nucleophilic regent, base catalyzed, it's primarily determined by steric accessibility, where the nucleophile can best reach less substituted carbon. But if the reaction has more electrophilic character, acid catalyzed, the nucleophile tends to add to the position that develops the largest cationic character, more substituted carbon if stabilized. It's a powerful and versatile tool in synthesis.
Our journey continues with electrophilic additions involving metal ions, like mercury or palladium.
Exactly. Certain metal cations, notably Hg2+ and Pd2+, are excellent at promoting these additions by electrophilically attacking alkenes. The addition is then completed when a nucleophile, either the solvent or a ligand attached to the metal, joins the complex.
Palladium reactions are important synthetically, right? But maybe complex.
Yes, Pd2+ reactions are incredibly significant. We'll cover them more in Part B, but they often proceed to further reactions like oxidation or coupling. Mercury products, however, are often remarkably stable, allowing for direct study of the initial addition step itself.
What about silver?
Silver ions are also interesting. They form complexes with alkenes. This is the basis for argentation chromatography, but typically Ag+ doesn't proceed to form stable adducts through intermolecular nucleophilic addition, though internal nucleophiles can sometimes be captured, leading to cyclization reactions.
So let's focus on mercury. Solvomercuration.
Right. Solvomercuration with the mercuric ion, Hg2+, as the cation, is the best characterized of these reactions. Here, the nucleophile is usually the solvent itself, like water or an alcohol, a process called oxymercuration.
Can you isolate the products?
Yes, the organomercury adducts can often be isolated, maybe as halide salts, but frequently in synthesis, the mercury is immediately replaced by hydrogen in a convenient follow-up step called reduction, often using sodium borohydride. The overall two-step process, oxymercuration reduction, results in a net addition of hydrogen and the nucleophile, like H and OH from water, across the double bond.
Where does the nucleophile add? Regiochemistry.
The regioselectivity here is usually very high and strictly follows Markovnikov's rule. The nucleophile, like the oxygen from water or alcohol, ends up on the more substituted carbon. Terminal alkenes, for example, often show over 99% regioselectivity. Dissubstituted alkenes also show significant regioselectivity, which can be enhanced by steric effects. Bulky groups on the alkene can push the regioselectivity even higher towards Markovnikov.
How does alkene structure affect reactivity? Is it like protonation?
Interestingly, no, not exactly. The reactivity of alkenes toward mercuration is governed by a blend of steric and electronic factors. Unlike simple protonation or halogenation, simply adding more alkyl substituents doesn't always accelerate the reaction.
Really? How so?
Well, dialkyl terminal alkenes are more reactive than monosubstituted ones, as expected, but internal dissubstituted alkenes are often less reactive than terminal ones. For example, 1-pentene is about 10 times more reactive than Z2-pentene and 40 times more reactive than E2-pentene. This reversal happens because steric effects can sometimes outweigh the usual electron-releasing effects of alkyl groups. Too much bulk around the double bond can actually slow down the mercuration dance. Table 5.6 shows this data.
What about electronic effects on styrenes?
The Hammett correlation studies for oxymercuration of substituted styrenes show negative rho values, around -3.1, which is expected for an electrophilic reaction, indicating that electron-donating groups on the styrene accelerate the reaction. A methyl group on the alpha position is slightly activating, suggesting electron donation outweighs its steric effect in this case.
What's the mechanism? Bridged ion again.
Mechanistically, oxymercuration can be described in terms of a cationic intermediate, either a bridged mercurinium ion, a three-membered ring with mercury, or an open carbocation, similar to other electrophilic additions. These intermediates can even be detected by NMR in non-nucleophilic solvents, providing direct evidence of their existence. The addition is completed by the nucleophile attacking the carbon atom that bears more positive charge within that intermediate.
Okay, stereochemistry, anti-addition.
Usually, yes. Oxymercuration of unhindered alkenes is typically a stereospecific anti-addition. This is consistent with a mercurinium ion intermediate that's opened by nucleophilic attack from the opposite side. Conformationally biased cyclic alkenes like 4-T-butyl cyclohexane also exclusively yield products of anti-diaxial addition, where the new groups, OH and HG, add to opposite faces and end up in axial positions.
Any exceptions? Norborne.
Oh, yes. Here's where it gets really interesting again. Norborne is a fascinating exception. It gives exclusively exosyn addition.
In addition, same side.
Yes. The mercury and the nucleophile add to the same face, specifically the exoface. Even with bulky substituents on the 7 position, like 7,7-dimethylnorborne, it still yields the exosyn product, defying the usual tendency for anti-addition.
Why does Norborne do that?
It challenges the simple bridged mercurinium ion model and strongly suggests an intramolecular transfer of the nucleophile from the mercury itself might be happening. For Norborne, the alternative anti-addition pathway is simply sterically restricted by its unique bicyclic structure. The endoface is too crowded. Other bicyclic alkenes also frequently show largely or exclusively syn addition, highlighting this alternative pathway.
Do polar groups on the alkene affect mercuration?
Yes, oxymercuration also shows considerable sensitivity to polar substituents. The general pattern is that the nucleophile adds to the carbon more remote from an electron withdrawing group. This has been explained by proposing that electron-withdrawing groups destabilize positive charge, so the unsymmetrical transition state where there's less positive charge near that substituted position becomes the most energetically favorable. Studies on substituted Norborne support this directing effect.
What do calculations say about the Norborne case?
Computational studies, DFT, on ethene suggest a symmetrical bridged pre-reaction complex, but the transition state for addition is actually very unsymmetrical, with the nucleophile, like formate, already partially bonding. For Norborne, the calculated transition state is looser, suggesting a 4-center syn mechanism. This indicates there's no strong energetic prohibition against syn addition, consistent with the experimental result.
How do they explain regioselectivity in Norbornes?
The calculations suggest regioselectivity in substituted Norbornes is a result of the double bonds polarization. The Hg2+ attacks the more electron-rich, more negative carbon. Calculated charges show this polarization increases significantly as the transition state is approached. Figure 5.5. Remote polar groups can also direct addition by differentially polarizing the two faces of the pi bond.
Okay, let's try to interpret mercuration overall. What's the big picture?
So what does this all mean? A broad mechanistic interpretation suggests that the Hg2+ ion is rather loosely bound in an initial complex before the rate-determining nucleophilic addition step. The bonding in the intermediate is weaker at the carbon that is best able to accommodate positive charge, which leads to Markovnikov regioselectivity.
And stereochemistry.
If there's little steric hindrance, anti-addition is preferred, likely via opening of a mercurinium ion. However, the syn mechanism is definitely available, especially when anti-attack is blocked, possibly involving ligand migration from Hg2+ to carbon. Crucially, it is the nucleophilic capture step that determines the final regio and stereochemistry, because the initial mercuration step itself can be reversible.
Anything else unique about mercury?
Yes, one interesting electronic feature is that the mercury-substituted carbon in the product actually bears some negative charge, which is a different electronic pattern from most other electrophilic additions, like halogenation, where the carbon initially attacked by the electrophile becomes positively charged.
Right. And briefly, argentation, Ag plus just complexation mostly.
Yes. Reversible complex formation between alkenes and silver ions is the basis for many analytical and separation techniques, like specialized TLC, HPLC, or GLC for separating unsaturated compounds. Their affinity generally decreases with additional substituents, but increases with strain in the alkene. However, the key difference from HGI is that Ag normally does not induce intermolecular nucleophilic addition, though internal nucleophiles can sometimes be captured, leading to cyclization. Computational studies suggest stronger complexation with alkyl-substituted alkenes in the gas phase, contrasting with solution trends and pointing to the greater importance of solvation effects in the liquid phase versus pure electronic polarization in the gas phase.
Now we come to a really important class of reactions. Alkyl-boranes and their synthesis and reactions, especially hydroboration. This is a cornerstone of modern organic synthesis.
Absolutely. Alkenes react with borane, BH3, and its derivatives, like alkylboranes, to form incredibly useful organoborane intermediates. Borane itself is electron deficient, usually existing as a dimer, B2H6, bridged by hydrogens. It readily forms stable Lewis acid-base complexes with electron pair donors like tetrahydrofuran, THF, or dimethyl sulfide, DMS, which are common ways to handle it.
So what is hydroboration? How does borane add?
The addition of borane, or its derivatives, to alkenes, known as hydroboration, is technically an electrophilic process because boron seeks electrons, but, and this is critical distinction, it's concerted.
All at once?
Yes, imagine a perfectly synchronized duet. The alkene donates electron density from its pi bond to a vacant p orbital on the boron atom, and simultaneously a hydrogen atom attached to the boron shifts over to the adjacent carbon atom of the original double bond.
So CB bond and a CH bond form at the same time.
Exactly. This results in an overall syn addition, meaning both the new carbon-boron and carbon-hydrogen bonds form from the same side of the double bond. It proceeds through a fleeting four-center transition state involving the two carbons, the boron, and the shifting hydrogen.
Does it add more than once?
For unhindered alkenes and BH3 itself, yes, the reaction can happen 3 times until all 3 BH bonds have reacted, yielding trialkylboranes, R3b.
Why is hydroboration so important synthetically? Who developed it?
Its immense synthetic value is largely due to the pioneering work of H.C. Brown, who won a Nobel Prize for this work. It truly revolutionized organic synthesis. The key is what you can do with the alkyl-borane product.
Like what?
The boron atom can be replaced by a variety of other functional groups, most commonly a hydroxyl group, making an alcohol, but also a carbonyl group, ketonic acid, an amino group, my air, or a halogen. And crucially, these replacement reactions occur with retention of configuration at the carbon where boron was attached.
Retention, so the 3D arrangement stays the same.
Precisely. This retention of configuration, combined with the stereospecific syn hydroboration in the first step, allows chemists to predict the structure and spatial arrangement of the final products with extremely high confidence.
And what about regiochemistry? Where does the boron add?
This is the other key feature. Hydroboration exhibits anti-Markovnikov regiochemistry, boron bonds predominantly to the less substituted carbon atom of the double bond.
Opposite to Markovnikov.
Exactly. This is wonderfully complementary to many of the cationic additions we just discussed, like hydration or oxymercuration, which favor Markovnikov products.
Any other advantages?
Yes, a big one. Because there are no carbocation intermediates involved in hydroboration, you don't have to worry about competing rearrangements or unwanted eliminations, which is a huge advantage when you're trying to build complex molecules cleanly.
Okay, let's delve into those hydroboration details more. Why the high regioselectivity for the less substituted carbon?
It's due to a powerful combination of steric and electronic effects. Electronically, boron is electrophilic, seeking electron density. Studies with substituted styrene show a weak negative rho value, Nectar 0.5, indicating boron adds preferentially to the more nucleophilic, electron-rich end of the double bond, which is usually the less substituted carbon.
And sterics.
Steric factors strongly reinforce this electronic effect, especially when forming trialkylboranes. The boron atom, especially with alkyl groups already attached, is quite bulky. Adding the second and third alkyl groups encounter severe steric repulsion if the boron tries to add at an internal, more crowded carbon atom. It's simply much easier, sterically, for the boron to approach and bond to the less substituted, more accessible terminal carbon.
Are there ways to make it even more selective?
Yes. Specialized, bulkier borane reagents show even higher regioselectivity. Common examples include mono and dialkylboranes like disimylborane or desexylborane. Perhaps the most famous is 9-borobicyclo-3.3.1 nonan, universally known as 9-BBN.
How are they made?
They are usually prepared by carefully controlled hydroboration of specific alkenes, like isoamylene, tetramethylethyline, or cycloctadiene for 9-BBN, using the right stoichiometry. These bulky reagents achieve incredibly high regioselectivity. For example, 9-BBN adds to 1-hexene with something like 99.9% preference for boron bonding at the terminal carbon, table 5.7.
What about stereoselectivity, adding from the less hindered face?
Yes, that's the general rule. Borane prefers to approach from the less hindered face of the double bond, leading to syn addition on that face. Simple borane, BH3 or its THF complex itself, isn't always highly stereoselective for unhindered molecules, sometimes giving mixtures if both faces are similarly accessible. Table 5.8 shows examples with cyclic alkanes.
Do the bulky reagents help here too?
Absolutely. Bulkier reagents like diastereomers or especially 9-BBN significantly enhance this stereoselectivity. For instance, with 7,7-dimethyl-norborne, which has one face clearly more hindered, 9-BBN shows a 97% preference for adding to the less hindered endoface.
Are there other types of boranes used? Haloborane.
Yes, haloboranes like BH2Cl, BHBr, BHCl2, or BHBr2 are also useful hydroborating reagents. They are often more regioselective than borane itself. Plus, the halogens can be replaced by hydride, using hydride reagents or other groups, allowing the preparation of unsymmetrically substituted boranes.
What about boranes with oxygen attached?
Oxygen-substituted malanes, such as catechol-borane and pinacol-borane, are also used. They are generally less reactive than alkyl or haloboranes because the oxygen atoms donate electron density to boron, attenuating its electrophilicity. This can be useful when you are in milder conditions or need to differentiate between double bonds. The reactivity of catechol-borane can be enhanced by additives like N-dimethylacetymide.
Is hydroboration reversible? Can the boron move around?
Interestingly, yes. Hydroboration is thermally reversible, particularly at higher temperatures, typically above 160 degrees C. At these temperatures, BH moieties can be eliminated from alkyl boranes, the reverse of hydroboration, but the equilibrium still favors addition overall.
What happens if it eliminates and readds?
This allows for fascinating boron migration along the carbon chain through a series of temporary eliminations and readditions. The boron essentially walks along the chain. This migration, however, cannot occur past a quaternary carbon, a carbon with no hydrogens, as that would block the necessary elimination step.
What's the result of this migration?
The outcome of this thermal reversibility and migration is remarkable. At equilibrium, the major trialkyl borane formed is the one where boron is attached to the least substituted terminal carbon. This isomer minimizes steric interactions and is thermodynamically the most stable. This provides a powerful means for thermodynamic control over the reaction, allowing you to isomerize an internal alkylborane to the terminal one.
When does this happen easily?
These migrations are especially facile for alkylboranes derived from highly substituted alkenes, like tetrasubstituted ones, occurring even at relatively mild temperatures, 50-60 degrees E, and they exhibit both regio and stereoselectivity, dictated by the relative energy of the intermediate borane-alkene complexes. Evidence suggests this is an intramolecular migration. Computational studies, figure 5.6, have even located a transition state for this, involving an electron-deficient pi complex, about 20-25 kilobarm above the trialkylborane, analogous to the bridged carbocations seen in carbocation rearrangements. The boron effectively hops down the chain via these structures to find its most comfortable, least crowded spot.
Okay, let's talk about the incredible synthetic transformations possible with organoboranes once you've made them. What's the most common reaction?
By far the most widely used reaction is the oxidation to alcohols using alkaline hydrogen peroxide, H2O2, and base-like NaOH.
How does that work?
The trialkylborane, R3b, reacts with hydroperoxide anion, HOO. This involves an initial coordination to boron, followed by a remarkable migration of an alkyl group from boron to the adjacent oxygen atom, displacing hydroxide. This happens 3 times, converting the trialkylborane into a trialkoxyborane, BOR3. This intermediate is then easily hydrolyzed in the alkaline solution to yield the alcohol, ROH, and borate salts.
And the stereochemistry.
The crucial point here, as mentioned before, is that the beta-O migration step occurs with retention of configuration at the carbon atom that moves. Combined with the stereospecific syn hydroboration, this means you can confidently predict the exact structure and spatial arrangement of the resulting alcohol.
And the regiochemistry is anti-Markovnikov.
Yes, because hydroboration puts boron on the less substituted carbon, and oxidation replaces boron with OH with retention, the resulting alcohol has the hydroxyl group on the less substituted carbon. This is wonderfully complementary to the Markovnikov alcohols obtained by direct hydration or oxymercuration reduction.
Are there other ways to oxidize boranes?
Yes, other oxidants can be used. Molecular oxygen can work, especially in perfluoroalkane solvents. Sodium peroxycarbonate, amine oxides like trimethylamine N oxide, and oxone are also effective, sometimes preferred for large-scale reactions.
Can you oxidize them further, like to ketones or acids?
Yes. Using more vigorous oxidants, such as chromium-free agents, like chromic acid, can replace boron not just with OH, but oxidize it further to the carbonyl level. For example, hydroboration of terminal alkenes with dibromoborane dimethyl sulfide complex, followed by hydrolysis and then oxidation, yields carboxylic acids. Internal alkenes can give ketones this way.
What about making alkenes instead of alcohols?
The boron atom can also be replaced by an amino group, converting alkenes into amines. Common reagents are chloramine, NH2Cl, or hydroxylaminosulfonic acid, H2NOSO3H.
What's the mechanism? Similar to oxidation.
It parallels the hydrogen peroxide oxidation very closely. The nitrogen reagent, which has a good leaving group, first adds nucleophilically at boron. Then, an alkyl group migrates from boron to nitrogen, expelling the leaving group, chloride or sulfate, again with retention of configuration. The resulting aminoborane is then hydrolyzed to free the amine, RNH2.
Can you make secondary amines?
Yes, secondary amines can be formed by reacting boranes with alkyl or arylazides, RN3. This works most efficiently using monoalkyldechloroboranes, which can be made from RCH-CH2 plus BHCl2 on E220. You can also use N-chloroprimary amines.
Can you turn boranes into alkyl halides?
Absolutely. Organoborane intermediates can also be used to synthesize alkyl halides. Replacing boron with iodine is rapid using iodine in the presence of base, like sodium methoxide and methanol. Less basic conditions involve using reagents like iodine monochloride, ICl, with sodium acetate. Bromination is also possible using bromine and base.
And the reactivity here.
Just like with the alcohol formation, the regioselectivity reflects the initial hydroboration. So hydroboration of terminal alkenes followed by iodination will give you primary alkyl iodides. This is the opposite regioselectivity to what you'd get from direct ionic addition of HI to the alkene, which would give the secondary iodide Markovnikov product. It's a great way to make primary halides from terminal alkenes.
Finally, you mentioned H.C. Brown. He also developed an enantioselective hydroboration, right? Making chiral alcohols.
Yes, a major breakthrough. Several chiral alkylboranes are available in enantiomerically enriched or pure form, and they can be used to hydroborate prochiral alkenes to prepare enantiomerically enriched alcohols and other chiral compounds. This is incredibly powerful for synthesizing drugs and other complex molecules where specific chirality is essential.
What's the main region?
The most thoroughly investigated and widely used region is bis isopenocamphaloborane, usually abbreviated as IPC2BH.
Where does that come from?
It can be prepared in essentially 100% enantiomeric purity from readily available alpha pine, a natural terpene found in pine trees. Crucially, both enantiomers of alpha pine are available, so you can make both enantiomers of the IPC2BH reagent, giving chemists amazing control over which enantiomer of the product they form.
How does it achieve selectivity? Why is it chiral?
The remarkable selectivity of IPC2BH comes from its specific, rigid conformation derived from the pine structure. It adopts a shape that minimizes steric interactions, and this creates a very precise chiral steric environment around the boron atom. You can picture the alkene approaching this chiral pocket.
So one approach is favored over the other.
Exactly. The model suggests that Z-alkanes, cis-alkanes, in particular encounter significantly less steric hindrance when approaching the boron in one specific orientation, transition state A in the Book's diagrams, compared to the alternative approach, TSB. This difference in transition state energy leads to very high enantioselectivity. For instance, Z2-butene undergoes hydroboration with IPC2BH with an astonishing 98% enantiomeric excess E. Other Z-dis-substituted alkenes also generally give good enantioselectivity, typically in the 75–90% E range.
What about E-alkenes or cyclic ones?
They tend to give much lower selectivity with IPC2BH, maybe only 5–30% E. The fit just isn't as good for those substrates.
Are there other chiral boranes?
Yes. Monoisopenocamphylborane, IPCBH2, can also be prepared enantiomerically pure. It reacts with a prochiral alkene to give a mixture of diastereomeric dialkylboranes. Often, one diastereomer is formed in excess, and sometimes it can be purified, for example by crystallization, to achieve extremely high enantiomeric purity before the oxidation step. Oxidation then yields the enantiomerically enriched alcohol.
Can you get the chiral part back? The pine?
That's a practical issue. Direct oxidation of the intermediate borane converts the expensive terpene-derived group, isopenocamciol, into an alcohol, making it non-reusable. However, there's a clever trick. Heating the dialkylborane intermediate from IPCBH2 with acetaldehyde cleanly releases the original alpha pine, which can be recovered and reused. A diethoxyborane derivative of the desired product is formed, which is then easily oxidized to the target alcohol. This makes the process much more economical.
Are there chiral haloboranes too?
Yes, chiral haloboranes like isophenylcamphoylchloroborane or the corresponding bromoborane have also been developed. They can provide moderate to good enantioselectivity, maybe 45–85% E, often best at low temperatures.
Wow. Okay, we've journeyed through this incredible, intricate landscape of polar addition reactions and their mechanisms. Now let's try to step back and tie it all together with some broad comparisons.
Yes, let's synthesize our understanding. What general trends and insights can we gain from looking at all these reactions side by side, from protonation to halogenation, sulfonylation, selenylation, epoxidation, mercuration, and hydroboration?
Have people tried to correlate these different reactions?
Yes, chemists have made various attempts to draw connections. For instance, Fukuzumi and Kochi found that when steric effects are carefully accounted for, there's actually a strong correlation between the rates of bromination and mercuration, suggesting similar underlying electronic influences are at play.
Any other correlations?
Others, like Nelson and co-workers, have found interesting correlations between an alkene's overall reactivity in various additions and its ionization potential, IP, which is a measure of how easily it gives up an electron from its pi bond. Often, these correlations show distinct lines or patterns depending on the substitution pattern of the alkene, mono, dibret, tetrasubstituted, reflecting how the different steric environments influence the approach of the electrophile.
Let's try to visualize this. Figure 5.7 in the text plots reactivity versus ionization potential. Can we walk through that in broad terms? Let's look at how reaction speed changes as we add more carbon branches, which generally lowers IP.
Okay, looking at figure 5.7 and the data in table 5.9. For protonation, represented by circles, the reactivity absolutely skyrockets initially as you add methyl groups, going from ethene to propene to 2-methylpropene. But then it sort of levels off or even drops slightly for the most highly substituted alkenes like 2-methyl-2-butene and 2-val-3-dimethyl-2-butene.
Why does it level off?
It suggests that the dominant factor controlling reactivity is the stability of the intermediate carbocation. Adding the first few methyl groups hugely stabilizes the carbocation, hence the massive rate increase. Beyond that, the stability gains diminish, or maybe steric effects start to counteract slightly. The degree of substitution at the more substituted carbon seems key. In Hammond postulate terms, protonation is very endothermic, so the transition state looks a lot like the high-energy carbocation intermediate. Carbocation stability is king here.
Okay, what about bromination? Squares on the plot.
For bromination, the reactivity also increases significantly with alkyl substitution. But here, the total number of substituents on the double bond seems more important. The rates continue to climb fairly consistently all the way from ethene through 2-methyl-2-butene.
So it doesn't level off like protonation.
Not nearly as much. This pattern is more consistent with a rate-determining transition state that's more symmetrical, perhaps resembling that bridged bromonium ion. In a bridge structure, all the substituents around the double bond can contribute to stabilizing the developing charge, leading to a more continuous increase in rate with overall substitution. It's a more even-handed stabilization.
What about sulfonylation and selenylation?
Triangle has. These are characterized by a much diminished sensitivity to substitution. The lines on the plot are much flatter. This reflects a smaller demand for electron donation in the transition state, less positive charge buildup, and perhaps an increased sensitivity to steric factors, which can counteract the electronic effects. The relatively low rate of styrene towards selenylation is a bit anomalous, possibly due to ground state stabilization and steric effects of the phenyl group.
Epoxidation hexagons using peroxyacetic acid here.
Epoxidation shows a trend somewhat similar to bromination reactivity, generally increases with substitution but with a reduced slope. And importantly, there's no clear evidence of a rate-retarding steric component becoming dominant. For instance, Z and E2-butene have very similar epoxidation rates, unlike in some other additions where sterics cause big differences. It's a smoother, more consistent tempo, less affected by crowding.
Mercuration, stars. That one seems complex before.
It is. Mercuration exhibits a pattern somewhat like carbocation formation initially. Rate increases from ethene to propene to 2-methylpropene, and 2-methyl-2-butene is more reactive than 2-butene. But then, a significant superposition of a large steric effect kicks in. Steric hindrance becomes dominant for the most substituted alkene, 2-butyl-3-dimethylbutene, causing its rate to drop significantly. This incursion of steric effects in mercuration has long been recognized. It's a dance that starts strong electronically but can get tripped up by crowding.
And finally, hydroboration, plus signs using 9 bbn here.
Hydroboration shows a completely different trend. Here, steric effects are dominant, and reactivity generally decreases with increasing substitution. The plot has a positive slope. This is likely due to the bulky nature of the borane regions themselves, especially dialkylboranes like 9BBN, and perhaps a decreased electron demand in the hydroboration transition state. It's a dance where the bulky leader actively avoids crowded areas. Similar trends are seen for dibromoborane and diisomborane.
So let's put that in perspective. The range of reactivity is huge, isn't it?
Absolutely. If you compare the relative rates for the least substituted ethene and most substituted 2,3-dimethyl-2-butene alkenes in Table 5.9, the ratio varies enormously across reactions. For protonation, the most substituted is maybe 111.4 times faster than ethene, but for 9BBN hydroboration, it's about 104.2 times slower.
Wow, that's a massive swing.
It beautifully illustrates the shift in dominant factors. From carbocation stability reigning supreme in protonation, all the way to steric effects completely dominating in hydroboration with bulky reagents.
Okay, let's look at this another way. Figure 5.8 arranges intermediates and transition states based on the periodic table. What does that show us?
Right. Figure 5.8 is fascinating. It tries to connect the structures of stable products, reactive intermediates, and transition states involved in these additions, organizing them roughly by the group of the key atom involved, like C and O halogens. It helps us see patterns in reactivity based on electronic structure.
So let's start on the left with electron-deficient species like carbon.
Okay. Group I in this context relates to electron-deficient species. The prime example is the open carbocation formed during protonation. We know these are highly reactive, and their subsequent reactions, nucleophilic capture, elimination, rearrangement, are typically controlled by electronic factors like stabilizing positive charge, leading to Markovnikov regioselectivity in additions, or Zaitsev elimination.
What else fits here?
Related electron-deficient transition states include those for hydroboration and perhaps protonated cyclopropanes. The hydroboration TS involves boron and hydrogen, and it collapses via a hydride shift from boron to carbon, driven by electronegativity differences in sterics. Corner protonated cyclopropanes rapidly rearrange to the most stable open carbocation, and we saw that mercuration has a related pathway where a ligand can migrate from mercury to carbon, synaddition, when anti-attack is blocked, somewhat analogous to hydride migration in hydroboration, with regiochemistry still dictated electronically.
Okay, moving across the periodic table. Cationic species with full octets.
Yes. Groups 2 or 3 here involve cationic octet structures like aziridinium ions, bridged nitrogen, and protonated epoxides, bridged oxygen. These are still electrophilic because of the positive charge, but the central atom, N or O, has a full octet, so they aren't strictly electron deficient like carbocations.
How does that affect their reactivity?
Ring opening of aziridinium ions is normally controlled by steric access for the incoming nucleophile, as nucleophilic participation is needed. However, we saw exceptions like sulfofluorination, which follow electronic control, Markovnikov, due to developing carbocation character. The O-protonated or Lewis acid-activated oxirane, epoxide, seems borderline, showing instances of both Markovnikov and anti-Markovnikov ring opening, depending on the exact substrate and condition.
And the neutral rings themselves.
Further over, groups 3 and high V, we have the neutral octet structures: cyclopropane, aziridine, oxirane, thiourane. Cyclopropane is quite resistant to nucleophilic attack. Aziridines and epoxides are successively more reactive towards nucleophilic ring opening, and the regiochemistry here is typically controlled by steric approach factors, attack at the less hindered carbon. Thiorenes are similar.
What about the bridged halogen ions, sulfonium, selenium? Where do they fit?
They fall into groups 3, 4, V involving bridging species. For chloronium and bromonium ions, for example in halohydrin formation, the bridging bonds are relatively weak compared to CC or CO bonds. Markovnikov orientation, electronic control, usually prevails in their opening, as the carbon better able to support positive charge takes precedence, though we noted exceptions.
But sulfur and selenium are different.
Yes. For sulfonylation and selenonylation, the bridging bonds in thyranium and selenoranium ions are stronger. Here, anti-Markovnikov regiochemistry is frequently observed because nucleophilic engagement, controlled by steric access to the less hindered carbon, becomes critical for opening that more robust bridged ring.
It's really insightful to compare the nature of the electrophile itself, too, right?
Yeah.
Like H plus versus Br plus I.
Absolutely. The proton, H+, is a hard acid. It's tiny, has no unshared electrons. It forms electron-deficient carbocations or maybe hydrogen-bridged cations. It's highly reactive, and its formation is often the slow, rate-determining step with fast nucleophilic capture afterwards.
But bromine is different.
Positive bromine, as in a bromonium ion, is a softer electrophile. Critically, it does have unshared electron pairs, allowing it to participate in bonding using potentially 4 electrons, 2 from the pi bond, 2 from bromine's lone pair. If we represent it as having 2 partial covalent bonds, it's electrophilic, but not electron deficient in the same way a carbocation is. Bromine retains its octet. This makes it a more strongly bridged and generally more stable species than what's possible for the proton.
How does mercury fit in? The mercurinium ion.
The mercurinium ion has similarities and differences. The electrophile, plus HGX or Hg2+, is a soft Lewis acid. It polarizes the pi electrons, forming what's often described as a 3-center, 2-electron bond, possibly with some additional back bonding from Mercury's filled d orbitals into the alkane's antibonding orbitals. This bridging is generally considered weaker than the 3-center, 4-electron bonding picture often used for a bromonium ion.
Is there a computational way to look at the bonding in these rings?
Yes, Kremer and Kraka use computational analysis focusing on bond paths and electron density within these 3-membered rings, related to figure 5.9.
What do they find?
They found that neutral rings like cyclopropane, aziridine, and oxirane are well described by the classic bent bond model, with CO bonds being less bent than CC bonds in cyclopropane. When you protonate the oxirane, the CO bonds start to bend inward more. But for a hypothetical bridged fluorine species, the calculation suggests there isn't really a true ring anymore. It looks more like a weak pi complex.
Why the difference?
It relates to the relative ability of the bridging atom to donate electron density back into the ring-forming orbitals. The order seems to be CH2 NHOO plus HF plus Bren. As the atom gets more electronegative or positively charged, its ability to donate electrons and form strong bent bonds decreases, weakening the ring structure. It shows how the nature of the bridging atom fundamentally changes the bond character.
Okay, we spent a lot of time on alkenes, double bonds. What about additions to alkynes, triple bonds, and allenes, cumulative double bonds? Are they similar?
Yes, let's briefly touch on those. Additions to alkynes share similarities with alkynes, as their highest energy electrons are also in pi-type orbitals.
But are they as reactive?
Generally, no. Alkynes are often less reactive than similarly substituted alkanes toward many common electrophiles.
Why is that?
There are 2 main reasons proposed. 1, the intermediate vinyl cation, a positive charge on a double-bonded carbon, is significantly higher in energy, maybe 10 kilocoulomb less stable, than an analogous alkocation formed from an alkene. 2, forming a bridged intermediate from an alkyne would require incorporating a double bond within a highly strained 3-membered ring, which is energetically unfavorable.
Does the rate difference vary?
Yes, it depends on the electrophile and conditions. Table 5.9 shows large reactivity differences between alkenes and alkynes for bromination and chlorination, alkenes much faster, but relatively small differences for protonation, hydration. Having a carbocation stabilizing phenyl group also reduces the difference for halogenation.
Do alkynes use the same mechanisms?
Yeah.
AD2, ADE3?
Yes, the basic mechanistic possibilities are similar. Reaction via a vinyl cation, a bridged intermediate, or a termolecular AD3 process. And a prior pi complex between the alkyne and the electrophile is often involved.
Okay, let's look at hydrohalogenation and hydration of alkynes. How does HCl add?
For aryl-substituted alkynes reacting with HCl in acetic acid, you often get mixtures of the vinyl chloride product and vinyl acetate from solvent capture. A vinyl cation intermediate stabilized by the aryl group is believed to be involved. An ion pair can collapse to the vinyl halide or be captured by the solvent. The addition is mainly syn.
What about simple alkynes?
Alkyl-substituted acetylenes reacting with HCl can proceed via either AD3 or AD2 pathways. The AD3 mechanism leads to anti-addition. Adding extra halide ions promotes the AD3 pathway and increases the overall rate. For example, 4-octine reacting with TFA in the presence of bromide gives mainly the Z-bromoalkene via anti-addition. The bromide greatly accelerates the reaction, suggesting it's involved in the rate-determining protonation step formulated as a concerted ADE3 process.
So less likely to form collocations compared to alkenes.
Generally, yes, because the vinyl cation is so much higher in energy. The concerted ADE3 pathway becomes more competitive. Even for 1-arylkynes, there's often a mix of AD2 and AD3, with AD3 becoming more important at high bromide concentrations or lower acidity. Interestingly, AD3 addition to 1-phenylpropyne gives the anti-Markovnikov product, likely due to steric effects of the phenyl group directing the proton away.
What about hydration of alkynes, adding water?
Alkynes can be hydrated in concentrated aqueous acid. The initial product is an enol, which rapidly isomerizes, tautomerizes, to the more stable ketone or aldehyde.
Are they less reactive than alkenes here too?
Somewhat less reactive, yes. For example, 1-butene is about 20 times more reactive than 1-butyne towards hydration. Reactivity increases with electron-releasing groups on the alkyne, as expected.
What's the mechanism? Vinylcation.
Solvent isotope effects again indicate that rate-determining protonation to form a vinylcation is the likely pathway. Reactions that proceed through vinylcations are generally not expected to be stereospecific because the spibridized binylication is linear and can be attacked from either side. Additions of TFA or triflic acid also give mixtures of syn and anti-products, consistent with a vinylcation intermediate.
Okay, how about halogenation of alkynes? Adding Br2 or Cl2?
This is generally slower than halogenation of the corresponding alkenes. If you use excess halogen, you can get addition across the triple bond twice, leading to tetrahaloalkenes.
Is it still electrophilic?
Yes, it shows electrophilic characteristics. For example, chlorination rates of substituted phenylacetylenes correlate well with sigma plus constants, Pareto-Exignev 4.2, and the reaction is typically second order overall.
Stereoselectivity, specific or not?
Often not very stereoselective. You can get significant amounts of solvent capture product too. This is consistent with reaction proceeding through a vinylcation intermediate.
Are there differences based on substitution?
Yes. For alkyl-substituted alkynes, mono-substituted ones tend to give syn addition, possibly via a very short-lived vinylcation. But dis-substituted internal alkynes often react via anti-addition and are also about 100 times more reactive. This difference suggests the transition state for internal alkynes is stabilized by both alkyl groups, pointing towards a bridge structure being involved, similar to alkenes. Bromination stereochemistry is usually anti for alkyl-substituted alkynes.
What about arylokynes and bromine?
For arylokynes reacting with bromine, an initial pi complex intermediate is observable. The kinetics are often third order overall, 83. The rate-determining step seems to be the reaction of Br2 with the pi complex to generate the vinylcation intermediate, and both syn and anti-products can be formed.
Does the aryl group influence stereochemistry?
Yes. If the aryl group has strong electron-withdrawing substituents, the reaction becomes stereospecifically anti. This is because the vinylcation is destabilized, making the bridged pathway dominant. The same is seen for simple alkyl alkynes like 2-hexene. Adding bromide salt can also push aryl-substituted alkynes towards anti-addition by intercepting the intermediate before it becomes a fully formed vinylcation.
So, can we summarize alkene bromination mechanisms?
It looks like an initial alkane-bromine complex forms. This can then, 1, dissociate to a vinylcation, especially if stabilized, e.g. by an aryl group. This leads to non-stereospecific products. 2, collapse directly to a bridged bromonium-like ion or react concertedly with a nucleophile, like Br or another Br2. This is dominant for alkyl-substituted alkynes and leads to stereospecific anti-addition.
Why are alkynes generally less reactive than alkenes then?
The lower reactivity probably stems from both the higher energy of the vinylcation intermediate and the greater strain involved in forming a bridged transition state containing a double bond within the three-membered ring. Also, alkynes might be slightly poorer electron donors, higher ionization potential, than alkynes.
Do calculations support this?
Yes. Computational studies comparing Br2 complexes with ethene, and even alene, figure 5.0, show that the initial complex structures and stabilization energies are quite similar. This suggests it's the subsequent step, forming the cationic intermediate, that's significantly harder for alkynes. Calculations also compare the stability of open beta-halovenine cations versus bridged haluranium ions, generally favoring bridged structures for Cl and Br, but open for F. They also find these ions are energetically difficult to form in the gas phase, consistent with the experimental need for polar solvents or catalysts.
Can mercury add to alkynes?
Yes, alkenes react with mercuric acetate in acetic acid. For example, 3-hexene gives the E product, anti-addition, while diphenylacetylene gives the Z product, syn addition under these conditions. The kinetics are first order in both alkene and mercuric acetate.
Is this used synthetically?
Yes. Mercury catalyzed hydration is a classic method for converting terminal alkynes to methyl ketones. The intermediate vinyl mercury compound undergoes protonation hydrolysis to regenerate the Hg2 plus catalyst. Mercuric triflate is a useful catalyst for this.
Okay, big picture for alkene additions. Key takeaways.
Understand the possibilities of both bridged ions and vinylcations as intermediates. Vinylcation processes tend to be non-stereospecific. Bridged ion or concerted ADE3 processes tend to give stereospecific anti-addition. In terms of relative reactivity, processes involving vinylcations, like rate determining protonation, are often only moderately slower for alkanes compared to alkenes, maybe reflecting the 10-15 kiloops mole higher energy of vinyl cations, partially offset by the higher ground state energy of alkenes. However, processes thought to involve bridged intermediates, like halogenation, often show much greater rate retardation for alkenes, likely due to the significant strain of incorporating a double bond into the bridged transition state.
Right. Lastly, for additions, what about allenes, those CCC systems?
Allenes are an interesting reaction type, related to both alkenes and alkenes with their cumulative double bonds.
Where does protonation happen, central carbon or end carbon?
You might intuitively think protonation would happen at the central spibridized carbon to form a potentially stable allylic carbocation. However, the surprising outcome is that kinetically favored protonation actually occurs at a terminal sp2 carbon, leading to a vinyl cation intermediate.
A vinyl cation. Why not the allylic one?
The reason is rooted in stereoelectronic effects. The allene structure is non-planar. The 2-pi systems are perpendicular. Protonation at the central carbon would initially lead to a twisted cationic structure that lacks the necessary orbital alignment for allylic conjugation. Calculations show this twisted structure is much higher in energy, maybe 36-38 kilocolmol higher than the vinyl cation.
So what products do you get from adding HX?
Consistent with terminal protonation, adding hydrogen halides to terminal allenes initially yields a vinyl halide. If conditions allow the second double bond to react, a geminal dihalide is formed, where both halogens end up on the same internal carbon. The regioselectivity of this second addition step generally follows Markovnikov's rule, as the first halogen can stabilize the carbocation intermediate by resonance.
What about hydration?
Hydration of allenes using strong acids in aqueous solution also converts them to ketones via an enol intermediate. This also involves initial protonation at a terminal carbon. Kinetic features, including the solvent isotope effect, are consistent with rate-determining proton transfer to form a vinyl cation.
And other electrophiles? Halogens, mercury.
In systems where bridged ion intermediates are expected, like halogenation or mercuration, nucleophilic capture generally occurs at the central carbon, leading to an allylic product. Examples include solvent capture in halogen additions or the structures of isolated mercuration products.
Phew. Okay, after that whirlwind tour of additions, let's gracefully switch partners to the other half of our molecular dance. Elimination reactions.
Right, time for the reverse path. Eliminations, as we introduced earlier, involve the removal of another molecule from a reactant. We're focusing today on polar elimination reactions, which involve heterolytic bond-breaking electrons staying with one fragment.
And usually forming a double bond.
Our primary focus is on beta elimination, where groups are removed from adjacent carbons, the alpha carbon bearing the leaving group, and the beta carbon bearing the hydrogen, to form a carbon-carbon double bond.
Are there other types?
Briefly, yes. There's alpha elimination, where two groups leave from the same carbon, often forming unstable species called carbenes, discussed in Part B, Chapter 10, and gamma elimination, where groups leave from carbons separated by another atom, often leading to cyclization via intramolecular nucleophilic displacement. But beta elimination is the key one for making alkenes.
Can we see some examples? Scheme 5.2 has some.
Yes, let's look at some representative outcomes. Dehydrohalogenation, the removal of hydrogen and a halogen, like HBr or HCl, is a typical example. For primary alkyl halides, a main competing reaction is SN2 substitution, where the base acts as a nucleophile instead.
How do you favor elimination?
To favor elimination over substitution, especially for primary or secondary substrates, chemists often use bulky non-nucleophilic bases like potassium terpetoxide, K plus OTBU. These large bases find it easier to pluck off a proton elimination than to attack the carbon center substitution. And importantly, these bulky bases often preferentially remove the less hindered proton, leading to the formation of the less substituted alkene Hofmann product.
Does it get complicated with secondary halides?
Yes, regiochemistry, which alkene isomer forms, for example, double bond position, and stereochemistry, EVSE alkene issues, can arise even with simple secondary halides depending on the base, solvent, and substrate structure.
Are there other useful bases?
Strong non-nucleophilic organic bases like DBU, diazabocycloundecene, and DBN, diazabocyclonone, are particularly effective, especially for substrates that ionize easily, like tertiary halides.
What about other leaving groups besides halides?
Dehydrosulfonation is another common example, involving elimination from alkyl sulfonates like tosylates, OTs, or mesylates, OMs. These are good leaving groups, but they generally give a higher proportion of substitution compared to halides under similar conditions.
Can nearby groups influence elimination?
Absolutely. A carbonyl group alpha to the hydrogen being removed can significantly stabilize the developing negative charge in the transition state, or even a carbanion intermediate. This facilitates elimination by weaker bases and precisely controls the regiochemistry, favoring deprotonation of the alpha carbon next to the carbonyl, often leading to stable conjugated iners.
And you mentioned the Hofmann elimination earlier.
Yes, the Hofmann elimination is a classic case. It typically involves elimination from a quaternary ammonium salt, where the leaving group is a neutral trialkylamine, like trimethylamine. This is a relatively poor leaving group, and it's also bulky. This combination leads to a strong preference for formation of the less substituted alkene-Hofmann rule, primarily due to steric factors in accessing the beta protons.
Okay, so we have these different outcomes. What are the underlying mechanisms? Are there different ways elimination happens?
Yes, to understand these eliminations mechanistically, we usually categorize them into three limiting mechanisms based on the timing of bond breaking and forming, E2, E1, and E1CB. These represent distinct ways the molecular dance of shedding partners can unfold.
Let's start with E2. What does that mean?
E2 stands for elimination by molecular. This signifies that two species, the substrate and the base, are involved in the rate-determining step. It's a concerted process, meaning everything happens in one perfectly synchronized step.
All at once. Base takes proton, CAC forms, leaving group leaves.
Exactly. Imagine the base approaching to pluck off a beta proton, and at the exact same moment, the electrons from that CH bond swing down to form the pi bond, and the leaving group on the adjacent alpha carbon departs. All three critical bond changes, CH breaking, CC forming, C leaving group breaking, happen concurrently in a single transition state.
Does the geometry matter for E2?
Critically. For an E2 reaction to occur efficiently, the hydrogen being removed by the base and the leaving group must be in a specific spatial arrangement, anti-paraplanar. This means they need to be on opposite sides of the carbon-carbon single bond and lying in the same plane, essentially pointing 180 degrees away from each other. This geometry ensures the orbitals, the sigma CH bond and the sigma CLG antibonding orbital, align perfectly for the smooth formation of the new pi bond as the leaving group departs. Syn-paraplanar elimination, where H and LG are eclipsed, is much rarer and usually higher energy.
What conditions favor E2?
Strong bases are needed to pull off the proton in the concerted step. Good leaving groups facilitate the reaction. Substrates that aren't too sterically hindered for the base to approach the beta proton work well. Primary and secondary are common. Polar protic solvents often favor E2.
What alkene product does E2 usually give? More or less substituted?
E2 often favors the formation of the thermodynamically more substituted alkene following Zaitsev's rule. This is because the transition state has some double bond character and is stabilized by alkyl substituents just like the final alkene product. However, if a very bulky base, like T-butoxide, is used, or if the leaving group is poor and bulky, like in Hofmann elimination, then steric factors dominate, and the base removes the most accessible, least hindered proton, leading to the less substituted alkene-Hofmann rule.
Okay, that's E2. What about E1?
E1 stands for elimination, unimolecular. The 1 means the rate-determining step involves only one molecule of the substrate. This is a two-step process.
What's the first step?
The slow rate-determining step is the unimolecular ionization of the substrate. The leaving group simply leaves on its own, taking its electrons with it, to form a carbocation intermediate.
Wait, that sounds familiar. Like SN1.
Exactly. It's the exact same first step as the SN1 substitution reaction. The substrate ionizes to form a carbocation. This means E1 and SN1 reactions are often competing pathways happening concurrently from the same intermediate.
So after the carbocation forms, how does elimination happen?
Once the carbocation forms, the elimination is completed in a fast subsequent step. A base, often a weak base, like the solvent itself, removes a beta proton from a carbon adjacent to the positive charge. The electrons from that CH bond then swing down to form the double bond, neutralizing the positive charge.
What conditions favor E1?
E1 is favored by conditions that favor carbocation formation. Good leaving groups, substrates that can form relatively stable carbocations, tertiary, secondary, primary, and polar proprotic solvents, like water or alcohols, that can stabilize the charged intermediate through solvation. Weak bases are typical, as a strong base would likely favor E2 instead.
Do rearrangements happen in E1?
Yes, absolutely. Because a carbocation intermediate is formed, it is susceptible to rearrangement, hydride or alkyl shifts, to form a more stable carbocation before the proton is removed. This means E1 reactions can sometimes lead to rearranged alkene products, which can be a clue that an E1 mechanism was operating. E1 typically follows Zaitsev's rule, forming the more stable, more substituted alkene from the potentially rearranged carbocation.
Okay, one more. E1CB. What's the CB?
E1CB stands for elimination unimolecular conjugate base. This is also a two-step process, but the order of events is critically different from E1.
How so?
In E1CB, the first step is the deprotonation of the beta hydrogen by a base to form a carbanion intermediate, a carbon with a negative charge and a lone pair of electrons.
A negative charge intermediate this time.
Exactly. This carbanion then, in the second step, expels the leaving group from the adjacent alpha carbon, using its lone pair to form the double bond.
When does this happen? Carbanions aren't usually very stable.
That's the key. The E1CB mechanism is favored under specific conditions. 1. When the beta hydrogen is unusually acidic, meaning it's relatively easy to remove with a base. This usually happens when there's a strong electron withdrawing group, like a carbonyl CO, nitro-NO2, cyano-CN, or sulfone SO2R, attached to the beta carbon, which can stabilize the negative charge of the carbanion intermediate through resonance or induction. 2. When the leaving group is relatively poor, if the leaving group were good, E2 might happen instead before the carbanion fully forms. 3. A reasonably strong base is still needed to form the carbanion initially.
So things like beta-keto esters might do this.
Yes, eliminations from substrates like beta-hydroxyketones or esters, nitroalkanes, or sulfones often proceed via an E1CB pathway, especially if the leaving group isn't great.
Is the carbanion formation always the slow step?
Not necessarily. The E1CB mechanism is often further subdivided based on which step is rate determining. E1CB. The initial deprotonation, carbanion formation, is irreversible and slow, rate determining. Leaving group departure is fast. E1CB, rev. The carbanion is formed rapidly and reversibly. It might get protonated back by the solvent. The subsequent departure of the leaving group from the carbanion is the slow, rate-determining step. You can sometimes detect this reversible first step by seeing deuterium exchange at the beta position if the reaction is run in a deuterated solvent.
So E2 is concerted, E1 involves a conjugation, E1CB involves an anion.
That's the essence of the three limiting mechanisms. But it's important to reiterate that these represent ideal limiting cases.
Meaning reality is messier.
Often, yes. The degree of CH bond breaking versus C leaving group bond breaking in the transition state can vary continuously. You can have E2-like transition states that have significant E1 character, lots of CLG breaking, little CH breaking, or significant E1CB character, lots of CH breaking, little CLG breaking. It's more like a spectrum or a continuum of transition structures, allowing for a range of mechanistic possibilities that blend features of these ideal types. Professor William Jenks depicted this nicely on a more Farrell-Jenks plot.
Why is understanding these mechanistic details so important then?
Because they are the key indicators for predicting and explaining how factors like the substrate structure, substituents, the strength and steric nature of the base, the quality of the leaving group, and the solvent all influence which reaction pathway is favored, and what the final composition of the products, alkene reagiochemistry and stereochemistry or substitution products, will be. Paying close attention to the likely nature of the transition state is like reading the precise choreography notes for each molecular elimination dance.
Okay, so we've really covered a lot grown today, haven't we? From the intricate dance of electrophilic addition to the reverse steps of elimination.
Absolutely. We've journeyed through the dynamic world of polar addition and elimination reactions. We've seen how tiny structural differences in the electrophile or the alkene can fundamentally alter reaction pathways, shifting from open carbocations to bridged ions, from syn to anti-stereochemistry, and from electronic control to steric dominance.
And then exploring the equally precise choreography of elimination, whether it's the synchronized E2, the two-step E1 via ication, or the carbanion-mediated E1CB.
What's truly remarkable, I think, is appreciating the exquisite precision with which molecules interact. It's all dictated by fundamental principles of stability, electron distribution, and, as we saw many times, steric hindrance. This isn't just about memorizing reaction names or mechanisms.
No, it's about seeing the underlying logic.
Exactly, seeing the elegance in how chemical bonds are formed and broken based on these principles.
So what does this all mean for you, our listener? This deep dive isn't just about understanding a chapter of advanced organic chemistry. It's hopefully about appreciating the incredible engineering happening constantly at the molecular scale. Think about the deliberate design behind many of these reactions when chemists use them in organic synthesis to build complex molecules.
Yeah, and this raises an important question, maybe something to ponder. Considering the deliberate design we see in synthetic chemistry, how might a deeper understanding of these precise controls over addition and elimination mechanisms unlock new avenues? Could it lead to creating novel materials with specific properties, or designing more efficient routes for drug synthesis, or even help us decipher the complex biological transformations happening within our own cells, which also rely on these fundamental reaction types?
That's a great point. The dance of atoms is truly everywhere, isn't it? And hopefully now you have a deeper understanding of its choreography.
We hope so.
We encourage you to keep exploring the hidden mechanisms and the intricate beauty of the molecular world around you.
Thank you for being part of our deep dive family and joining us for this exploration.
Until next time, keep digging into the details.